Well, good morning. Certainly it's morning here still. This is the research vessel Falcor operating in the Gulf of California, specifically in the South Pescadero Basin of the Gulf of California. And this is ROV Sebastian 0465. We are descending to a depth of most of the way down. It's at 3,000 vicinity of a hydrothermal vent field here in the South Pescadero Basin. A vent field that has formed as part of the rifting and the initiation of the continental rifting and the transition into seafloor spreading in this basin. Driven by the intrusion of volcanics into the subsurface. The vent field that we will be working near and across is called JaichMaa. It was discovered from ROV Falcor in 2018, 3 years ago, using autonomous underwater vehicles to do high-resolution seafloor mapping or meter-scale mapping. That allowed us to find the features associated with the hydrothermal vents, the edifices that form where those vents come out. And if you saw our ROV dive yesterday, about half of that involved successfully achieving some vent fluid sampling the water that's coming out of these vents. The JaichMaa vent field consists of several pretty large edifices, each about 20 to 25 meters high and about 50 meters across, made up of carbonates that precipitate out of the vent fluids that come out. The vent fluids come out at about 270 to 275 degrees Celsius. And they are saturated with minerals that have been dissolved in the subsurface. And then as that hot water hits the ambient cold water, that's about 2 degrees Celsius, the minerals precipitate out and form the chimneys and ultimately the large edifices. Here at this vent field, these are largely formed of carbonates rather than polymetallic sulfides. And that's because of the interaction of the hydrothermal vent fluids with the sediments that blanket the seafloor here. This is a heavily sedimented basin just undergoing the beginning of seafloor spreading. My name is David Caress. I'm the chief scientist on this leg of this expedition. The expedition is FK 210922. It's the designation, and it's an interdisciplinary investigation of the venting here in the South Pescadero Basin of the Gulf of California. My co-chief scientist is Raquel Negrete Aranda of the Institute CECESE in Ensenada, Mexico, and she will be taking over from me as we come on bottom and start getting into her work or her group's work. I'm a specialist in seafloor mapping. Raquel's group works on heat flow, and what we are going to be doing today, all day long, we hope, is to measure heat flow on several transects across and along this vent field. And that's measuring the conductive heat flow. That is the heat that is coming out of the seafloor by conduction at places close to and far away from these vents. Of course, the vents themselves transport a huge amount of heat in the fluids, and that's advective heat transport. We're very interested in the conductive heat, the pattern of conductive heat flow out of the vent system because that tells us a lot about what's going on in the subsurface. We're orienting these heat flow measurements along subbottom profiles that were collected with AUVs 3 years ago. And so a subbottom profiler is a sonar that provides an image of the subsurface. It runs at a relatively low frequency of 1 to 6 kilohertz, and it provides an image of the subsurface to about 50 meters depth or so. So with that, we have an idea of where the faults are that are breaking the subsurface, and in some cases breaking all the way to the surface and being expressed in the bathymetry. Where we're going to start out this morning is about 500 meters west of the vent field at a spot that's just about 50 meters past where one of these faults breaks the surface. And then we're going to start making heat flow measurements out here, and we'll make them along that subbottom profile track line all the way across the vent field, working towards the east. We're now at a depth of 3,281 meters and counting. And we expect to reach the seafloor in about 450 meters or so. The ROV descends at a rate of about 25 to maybe 30 meters per minute. You'll sometimes see that the pilots will stop and give you some great video of some of the animals that we see in the mid-water as we descend. When they do that, the winch that's paying out the tether continues to pay out the tether at the same rate. And so they'll slow the descent or stop the descent of the ROV for a minute or two so they can get that great footage, and then they will zoom down and catch up with the amount of tether that's been paid out. So when they do that, it doesn't actually slow our overall descent time. Well,
This chat function isn't working properly. I'll bring this one over.
if you watched the ROV dive yesterday, and the first part of it where we were doing the fluid sampling, that was at the central edifice of this vent field called Te Uja. The transect we're going to be working on today will run close to a pair of edifices that are adjacent to one another that's north of Te Uja. So we're about 150 meters north of where we were working yesterday. Those are called Moopt Mapan. I am not very good at pronouncing words in the Kilwa language. All the vent features have been named in the language of the Kilwa people of Baja California. So those two edifices are called Moopt Mapan and Tai Mapan, little sister and big sister. Where we were yesterday is called Te Uja, which means big cave. And if you watched that, you saw both a lot of the chemistry of these hydrothermal vents, and you also saw us spend quite a lot of time, a couple of hours, working hard to get good vent fluid samples. I'm very happy to report that that sampling was successful, and we have two what are called gas-tight samples that contain not just the water, but also the volatiles, the dissolved gases, sealed from those fluid samples, and we also have a large volume of unsealed, what we call the major samplers, and it seems to have worked well. And so we ultimately, after those samples get back to the labs on shore, we will have a knowledge of the chemistry of the fluids that are coming out of that particular vent edifice. We're now at a depth of 375 meters. And in about 150 meters, we'll start to see the bottom in our altimeter.
I'm saying, I can give you a little bit to say about water samples.
You want to step in and say?
No, it's brief. That even though the major samples like gas type can only do no better than this, that was one of the gaseous samples that I've ever seen that just fizzed the whole time. So the gas types don't have lots of gas. And we collected a few rock samples of living little chimney from the same place we sampled. Just talk about
Okay. Dr. Robert Zierenberg, or Z, was just filling me in on a couple of details to pass on to you all about the water sampling. First off, he said that the fluids from the major sampler, one of the reasons we know that those fluids were good, that we really got the vent fluids and not ambient water, is that it smells terrible. It smells of hydrogen sulfide. But the other thing he just commented was that was one of the fizziest vent fluid samples he's ever seen, which means that there were dissolved gases in the solution that then, as it was opened up here at atmospheric pressure, then that outgassed off, fizzing like a soda does, like carbonated water does. What do you think those gases are, Z?
mostly CO2, a little H2S.
Okay.
And then methane.
Okay.
Minor amounts of methane.
So, and though the chemistry hasn't been tested yet in the lab, the expectation, what Z just said, is that the majority of that gas fizzing out was CO2. What we were smelling is hydrogen sulfide, so there's hydrogen sulfide gas in there as well, and then there's probably minor amounts of methane. Okay, we are now at a depth of 3,440 meters. Still coming in on to bottom. So in the chat, I see a comment about the mirror pools. So yes, if you didn't watch it yesterday, yesterday's dive, if you go back and look at about 2 to 3 hours in, you'll see footage that's some of the best examples of venting with flanges that produce what we call mirror pools. That's how it's described in the chat. And this is where the hot vent fluid has formed, rather than vertical chimneys, it's formed flanges that stick out sideways. And then as the fluid comes out, it runs under those flanges and then cascades upward. So you get an underwater waterfall, upward waterfall kind of effect. But it also means that in those spaces underneath those flanges, you have the hot fluid that's trapped, because it's buoyant relative to the ambient water. And because of the heat and the composition, the density of that vent fluid is so different from the ambient water density that optically, in terms of looking at it with a camera, the surface, that boundary between the ambient water and the vent fluid, forms effectively a mirror. And so that's just really, really striking in the video. And we had many good examples of that yesterday. And in fact, when we water sampled, we used that by sticking the nozzles of the water samplers up into one of those mirror pools. So that assured us that what we were sampling was 100% vent fluid and not mixed at all with any of the ambient water.
Can I enter?
So Z is going to.
No, I'm just going to inject real quickly here.
Okay.
So those flanges, there were several of them. They're really kind of the equivalent to hot spring terraces, only upside down. If you ever been to like Mammoth Hot Springs in Yellowstone, you'll see there's a series of pools, little waterfalls. So here's something that's really cool to do. If you're watching this on a laptop, play the video, turn it upside down, and it'll look just like a hot spring with water coming out and going down the waterfalls. But because the buoyancy is in the opposite direction, the water's going up instead of down. So if you're watching the film on the laptop, try that. It's pretty cool.
Thank you, Z. All right, we're now at 3,520 meters. And I think in 2 or 3 minutes, we're going to be seeing the bottom in the altimeter. Oh, there was a comment there, ran all the people out of the room with the smell. Well, it is a really strong smell, but where we do that work is in the wet lab on the ship. And the wet lab does have proper hoods that safely ventilate. So we stick these very smelly materials into the hoods, run the hoods, and then actually we are well protected from the noxious fumes. And if there's too much hydrogen sulfide, of course, that's actually toxic. So, but we are very much properly set up to do this kind of work on this ship. Well, 3,555 meters and counting. We do have an altimeter reading, so we're now 90 meters off of the seafloor. All right, and then okay, we're coming into 3,600 meters here, and we're at about 50 meters above the seafloor. So when we drop in, which is 500 meters or so west of the vent field, it's going to be pretty much a flat, muddy bottom. And as we do the heat flow transects, the measurements that we're making are done with a probe that is mounted on the side of ROV Sebastian, on the starboard side. And it's about 60 centimeters long, so not terrifically long. It has 5 temperature sensors in an array along that probe. They're called thermistors, and they are high temperature sensors, so they can handle the really hot ground that we get in the vicinity of the vents, where temperatures again are the fluids coming out are at about 270, 275 degrees C. So we will set the ROV down. We will have, with a manipulator, at least in some sites, we will grab a rod that we will use to probe the seafloor to be sure that it's soft enough to insert the very delicate probe into the ground. When that's established, we'll move over to where we probed. We'll use a hydraulic ram to carefully insert the heat flow probe into the ground, and then we will take about 15 minutes, maybe as much as 20 minutes, to do the measurement, depending on how much of the complete measurement we do at that site. So the first thing is to just wait for the probe to come into equilibrium with the subsurface temperature. And what happens now we are just seeing the seafloor, and as predicted, it's a pretty muddy, flat seafloor out here. Of course, some benthic animals around. So when this probe goes in, it will get temperature readings off of the 5 different thermistors that are on it, and the ones that are deeper will be higher because the temperature increases as you go into the ground. What we're interested in measuring is the gradient in that upper surface. And if we know that gradient, that thermal gradient, and we also know the thermal conductivity of the material in the subsurface, the near subsurface, then we can calculate the heat flow out of the ground. And the heat flow team is going to be doing that in real time. In some places, probably about half of the stations will do a thermal conductivity measurement, and for that the heat flow probe has a heating element, and we turn that on. We put a pulse of heat into the ground, and then we look at how long it takes for that heat flow for that heat signal to decay away as the heat conducts away from the probe. And so when we do those measurements, the whole site will take a little bit longer, as much as 20 minutes. If we are just doing the heat, the temperature gradient measurement, then it takes a little bit less than 15 minutes or so. So now we are on bottom, and they are maneuvering over to the first heat flow site, which is about 20 meters to the south of where we started out. And what's going to happen now is that I am going to be handing off to Raquel Negrete Aranda of CSESE, who's the leader of the heat flow team. And she's going to be running the great majority of this dive. Good morning.
Good morning. Thank you, Dave.
Yeah. Thank you.
Hello, everybody. Good morning. So we're just gonna start this dive, which will be entirely devoted to do heat flow measurements. And so happy to see everybody joining in. Don't be shy if you have any questions. We will try to make this as interesting as possible. I think yesterday the overlays that John put it on the screen, during the measurements and showing the bathymetry were well received by the community. So thank you for that. And so we're just trying to find a spot where we're gonna position the ROV to do our first measurement. And in this spot, we might also get a push core. I'm not sure yet. Okay, so switching to Spanish now. Bueno, bienvenidos todos a esta transmisión en vivo, 21 de octubre, a bordo del Falcor. Soy Raquel Negrete del CISESE, líder del grupo de flujo de calor. Estamos a bordo del Falcor y este buceo va a estar enteramente dedicado a las mediciones de flujo de calor. Entonces trataremos de hacerlo lo más entretenido posible. Creo que las pantallas que se pusieron ayer durante el streaming live funcionaron muy bien, mostrando la batimetría y el curso de las mediciones. Así que si tienen preguntas, mándenlas por el chat. Vamos a tratar de hacer el mejor esfuerzo para contestárselas. Así que un saludo a toda la comunidad hispanoparlante. Un placer tenerlos por aquí. Y aquí vamos a estar un buen rato. Así que gracias por su presencia. Good morning.
So we are at the location on the bottom time is 3 p.m. Oh, okay. So I'm going to a sample here. Is it 50 meter spread? Well,
So we're
right now, location.
yeah, here.
Okay.
Okay. So the waypoint that I think which is the waypoint that we want to start at? Is that the waypoint 3?
No, it's the point that's 23 meters. It's that green point right there.
Okay, yeah.
So that I went and I triple checked that this morning. That is 50 meters east of the vault.
East.
No, it's going to be 50 meters west of the vault. Yeah.
Yeah.
We're basically on that location now. So do you want to take a sample here, or is it 50 meter spreads each time?
Would you think it would be a good location for the push core for Ronald? You know, the other pistol
I brought
one?
him this morning.
Yeah.
Yeah, let's take it. And we can always, we have plenty of bags, we can take the board, so let's take one here, it's a good position, yes.
Yeah. Let's take a push core first.
First, just the one.
Just the one. Just make sure that it doesn't go. That it survives, please. Okay, so we're going to take a push core here for Dr. Ron, who was the leader in Leg 1, and yes, absolutely. And so we will try to make this push core here, and then we will proceed with the heat flow measurement.
Thank you.
Manet va a ser el B. Sí. Okay.
Sample report, that then just about the samples. So I knew they were right there. Got some buttons here, so that's.
That's an update waiting over.
ROV Bridge, updated waypoint, thank you.
So as you can see, pilot just picked up the bottle and is going to proceed to take the push core. Let's see how soft the sediment is in this area. I'm thinking it will be probably soft, as softer as in the first transect. Eso es lo que va a pasar con la sonda aquí. ¿Te fijas cómo se hace como que se cae el sedimento? No me sorprendería que volviera a pasar luego el wiggling. Nice.
Like halfway up, alright. We're doing forward.
Well, that's cool.
Not
Let-
full like halfway.
We can dump and do it again.
Yes, I think it will. Yeah, the problem is that this sediment is too soft.
Yeah, so.
Yeah, let's try this time and
Oh,
so that's what's probably also happening with the ROV freeze. The last station we did yesterday, we had problems in starting all the way down. I mean, it was down.
Readings though.
Yeah, but the thermistor were reading water, and it's because that happens as well. That you know.
Notice when I set down to your super JaichMaa. So light, fluffy.
Right, right. So yeah, this area might present that challenge, but as we move towards the bend, it should be okay.
I'll do my best to get you.
Sure, thank you. ¿Qué tanto se va al fondo?
I'm not going to say.
So the first push core that we tried was filled only to half of halfway of the bottle. So hopefully we'll get a better the complete push core. But the sediment is not helping. It's really soft and it's easy for it to go just out of the bottle. Push container.
That looks like it's full.
Yeah. Yeah, it's good. Thank you.
When we take these push cores, are you worried about the surface sediments much, or you're trying to look at lower sediments, right?
Yeah,
So we can go a little bit deeper with some push cores are like this.
the surface. No, I think yeah, for our purposes, it's okay. Yeah, yeah.
I think when we get to that harder level, we'll get a better.
Right. This is probably the only push hook that we'll take today. I'm not sure. I'm not. They're still debating where to, but yeah, we need to do this because the one that they just yesterday didn't make it to the surface. So.
Did you want to take a second one here, just for redundancy?
I think one is good. En el Slack hay un nuevo grupo, ¿no?
That's it, yes.
¿Cuál es?
Sí.
Ah, ya lo vi.
Definitely Chris is on.
Those are my
Definitely Chris's fault. Yeah.
¿Qué?
those are my
Ah, sí. So I don't think we will need to poke here.
No. That was our poke test.
Exactly.
Can you switch on the pro, please?
Yes. Yep. You got it. Alright,
It's on now.
So we're getting ready for the first measurement.
pretty confident that one will make it all the way up.
Yeah, please. Thank you, Chris.
ROV bridge. Yeah, go ahead, Luke. Yeah, I'm just having some trouble gaining momentum going in that direction, so just inching the heading over to starboard a little bit to try to help us move.
Sure, yeah, that's no problem.
Okay.
You-
Even if you're going slow, we're still taking a sample here. I just thought to get you on the move.
Yep, that's great.
Okay.
Thanks.
And you say you're doing starboard, sorry?
Yeah, just not much, like 5 degrees.
But-
Take our heading around a little bit to help us get pushed over by the wind.
Yeah, that's fine.
All right.
Okay,
Cheers.
just don't move right now because the measurement is on its way and
We're not moving.
okay.
He's coming very slowly across.
Oh,
but we've
okay.
got a good double.
Okay. Oh, all right. Just making sure.
So, how fast are we probing?
Just the way you've been doing it. Yeah.
Are you ready?
No, we'll. I'll let you know in a
Was that a?
tomorrow. A few seconds.
Was that a that y'all did before? What did you say that? What was that a?
Okay,
Yeah,
probe
just,
in, please.
Okay, we're coming down very well. Actually, we have a yeah.
Okay, so as you can see on the screen, the thermistors have stabilized, and so the probe is actually going in. And all the way down, please. Okay, perfect.
Looks nice, thanks.
Yeah, great. Yeah, we have a thermistor in. As you can see on the graph, they just registered the heat from the friction. And yesterday, you know, the uppermost thermistor, which is the yellow signal, was flat.
Yeah, I seen that. Just missed
So
it.
yeah, so when that's happening, it means that it didn't went in.
So you're saying yellow is the friction?
No, the yellow one is the topmost thermistor.
Oh, okay.
And so
It
when
must have been sitting like this.
yeah, and or you know, when the probe goes in and it's such sediment that it can create like a hole, and then
Okay.
the work just comes in, and it's not.
And you don't get the reading.
And you don't need the reading. So you see that it's just the curve that will the decay from the friction created from inserting the probe. So we will wait a few minutes, and then when it's stable, flat, all they're flat, then you fire the pulse from the probe itself, and then it's you will see another big peak, another spike, and then it will. That decay is the one that gives us the information to calculate the thermal conductivity and the thermal gradient, the temperature gradient. And with that data, we
That's
just
how long it takes to cool back down. Is that
yes,
what it is?
exactly. So. Okay.
How far is the next move?
It's gonna be 50 meters.
To a fall. It's very
Yeah.
low. Well, no, very low.
Dani, ¿te puedo pedir un favor? Por favor, Robin, porque es necesito mi cálculo, pero ya casi no va a tener ella. Sí, entonces, a mí en mi cuarto, cuando nos cabina estaba el conector, y adentro de mi mochila está el cargador.
El conector está en el escritorio
En el escritorio, tú lo vas a ver luego.
y en la mochila y la laptop
Es la laptop está en la
So we have all the clearance. So there. Do you see the dimensions too?
Oh, okay.
So yeah, obviously.
So is that because the vibration is keeping it up a little bit? Or it's just
I don't know if it's enough. That's the
Okay, I'll do a quick summary of what I just saw in English, and for Lara and all the Spanish speakers, I was explaining to the pilots what the graph means. Ok, so la gráfica que ven muestra cada línea de color es uno de los termistores. Acuérdense que un termistor es básicamente un sensor de temperatura. Entonces, el primer pico que vemos es el calor registrado por los termistores. Al insertar la sonda se crea fricción y esa fricción crea calor y eso es registrado por los termistores. Como ven, después de la subida, los termistores, dependiendo de su ubicación en la sonda, empiezan a aplanar la curva, ¿no? Entonces, después de un cierto tiempo, esperamos para lanzar un pulso de calor, y con ese pulso de calor lo que vamos a ver es exactamente cómo decae la temperatura en cada termistor, y después de unos 7 minutos aproximadamente, con esa información podemos calcular el gradiente de temperatura, las propiedades térmicas del sedimento como la conductividad térmica, y de ahí podemos calcular el flujo de calor, que es la idea. Espero que haya sido claro, Laura.
Then you get a temperature for a sediment in situ temperature. Okay. So actually with the features of the here again. It's fine. In the case it's around 7 minutes, that's what it's usually needs.
I was just observing the vibration. ¿Por qué?
And it's usually not, it's a heat wire. We have, there's 4 or 5 wires. Each thermistor has a wire, and then you have in the middle one heating wire.
Okay.
¿Por qué? Porque se ve la vibración.
Por ejemplo,
Hay mucha corriente.
Huh. So there are some really small animals right along the ground, is that right?
Yes. Oh, oops. Oh, I'm sorry. I'm so bad with the camera. Okay. I wanted to zoom in. Oh, that's
The other zoom in.
yeah. That's it. That's a full zoom.
Okay. Those look like very small anemones.
Yeah,
but
the little
they must
ones.
only be a few millimeters across.
Yes. It's tiny, tiny. Gracias, muñeca.
Sí, era así.
Sí, perfecto.
Looks like the heat pulse has gone in.
Yeah. Thank you. So continuing with the explanation on what's going on the graphic, that's the heat pulse that's been fired inside the probe that has a heating wire just in between the thermistors. And as you can see, it decays very fast. And we will wait another 7 minutes or so to finalize the measurement.
this is like a
Yeah. And basically, it's what you're pulling out is the thermal conductivity.
yes, in this case, yes. Yeah.
Has there been much variability in the thermal conductivity values you saw?
It's actually the same. It's also the same for requirements. It's 75.
That's my baby.
It's not going to cruise a lot. It's beautiful. It's made.
It's actually a boy. It's Kai. Yeah, I know.
Maybe 0.5. Depending on where the sun is. So the sun impacts the sediment.
Oh my god.
That's mine.
That's a lovely picture. Oh my god, look at his face. such a.
Oh my god.
How old is he or she? 5, 6, just like that. Yeah. Right. Oh my god. They're beautiful. And your girl? Oh my god. What's his name?
Nelson. Lord Admiral Nelson has to letter.
Okay.
So I'm gonna disappear. I gotta go do an interview and such. If you need anything from me,
Sure,
you know,
sure.
I'm not gonna be far away.
Can you hear at 2? I'll be I'll be doing a shift to shore.
Oh yeah,
So
yeah,
can you take over for
yeah.
me?
And then it's off bottom at 3
At 3?
because we're an hour earlier.
Yeah, they. Okay, whatever.
We were supposed to be off bottom at 4 yesterday. Today
Yeah.
it's definitely 3.
I thought it was 3:30, but okay, that's okay.
Wow.
Now at least we have a clear idea.
Yeah.
of
So
the
as,
time.
as we get closer to that, we'll kind of modulate things so that we end gracefully.
Okay. So yeah, the ship to shore will be at 2, and so I'll be narrating, and our plan is to come here and just say hi to everybody just real quick, and then just go here.
Okay.
So I need you to be here sitting and everything.
Okay. So that starts at 2.
Yeah.
So you need to be over there at 1:45. So I need to be here at 1:45.
Okay. Yeah, good idea. Thank you. Okay, I'll let you know if
Yep.
anything comes up. Thank you.
All right. Thank you.
What's that?
I was asking what time we were off at.
3.
Off that.
Oh, the company, you know that? Oh, pretty close after.
So it was. Yeah. It's at 15.
You started already?
No, I just right before I got to the bottom.
Getting up there, time rolling.
Hello, Carl.
How's life?
My dog's name is Kuiper. Kuiper, but it's Kai for short. And it's actually an astronomical name because it's out of the Kuiper belt, the asteroid belt.
Yeah.
So yeah, we used to have 2 kids, this sibling from the same litter, but she died. She was born with a defect on a diaphragmatic hernia, and she died when she was 1. And so her name was Thea, which means the bodily that was supposed to crash with the moon, with the Earth, in the early stages of the solar system, and then gave birth to the moon. So it's like the moon's mother. So they are very scientific, names.
Let's go ready for your ducks.
Okay. Get the
Okay.
probe out, please.
So about this, thank you. No, ¿tú abres el Slack en el browser o tienes la aplicación?
That's our workshop.
Oh, that'd be cool. All right, that's.
Thank you.
Okay, so
I don't think I know. That's wrong. Ready? All right, moving
Okay,
along.
moving along, please. 50 meters.
Yeah. Yeah, close the shirt.
¿Cuánto crees que va a ser?
Uno. Just one through water. ROV bridge. Go ahead. Are you going to want us to stop at that waypoint? Just because it's taken a lot for us to gain and stop momentum today, so.
Yeah, let's do this. I'll keep you moving till about there.
Okay, perfect. Thanks. Is it going to be 50?
It will change.
It will change.
Yeah, so once we have the data, we will, I think, between 50 and then maybe 100 meters. And then once we get closer to the field, I think we do 25 meters.
Okay. Yeah, just let me know when you want us to.
Sure.
Whatever you want us to do.
Yeah, yeah, we'll let you know.
Thank you.
So
See that?
the thing is that we decide on the fly depending on what we're getting and if
Oh, what
it's
the results are?
yeah, because if it's changing like a lot, and then we can shorten the spacing.
Okay.
If it's staying the same, then we can just go faster. That's why. Okay, so we moved 50 meters towards what we believe is a fault escarpment in this area, and so we're setting up for doing another heat flow measurement here in a minute once they park the ROV. Nos movimos de la primera posición a 50 metros hacia el este, siguiendo la línea del transecto que va este-oeste, bueno, oeste-este en este caso. y nos estamos deteniendo en lo que creemos que es justo una estructura, el escarpe de una falla, y vamos a ver qué resultado tenemos aquí.
Is the probe on?
Probe is on, correct? I'll keep it moving over here. So, yeah. Yep.
So soft.
Yeah, it's so soft. We're actually trying to lay off.
Your part, right?
Yes, we're marking.
Okay.
That's fine.
Okay, probe in please.
Okay, probe coming in.
Muy bien, entonces estamos insertando la sonda ya después de que se reequilibraron todos los sensores y vamos a ver si todos se insertaron en un minuto, que me parece que sí. So after thermistor reequilibration time, we inserted the probe again, and it seems they are all in. All the thermistors are in. Remember, this is crucial for our measurements. So we will see what happens. It's going to be a full measurement though, so. Esa completa, ¿no? Yes.
I was just looking at the, you probably, if you go back up to here.
Mhm.
So like 15 minutes ago, Jenny noted to go to the bottom. Well, I think. Oh,
Okay.
it's,
Oh,
you haven't looked at that before.
no, yeah.
Anyway, but Jenny had just noted that you were talking about zooming in on something, and it wasn't what was shown on YouTube. So I just wanted to be sure you knew this is what they see on YouTube, is this display.
Oh, okay. Okay.
That's all. So you don't need to actually read through it.
No, but that's fine. I mean, so I could know. Okay.
Yeah. I
Yeah,
did the
I
same
see.
thing. I thought I was looking at the right thing, and I wasn't.
Ah, okay.
And that's where,
And you can Carl, you can put that picture.
yeah, they can put anything you want in there, but that's how you know what's being
Yeah,
shown
right.
on the YouTube.
Thanks.
Are you on the biology line as well?
No. Just heat flow. Manette is going to the one that will be staying on, but Isabella
Are you
is.
staying?
No,
No.
I'm not good speleologist. I don't know anything about animals or creatures.
Are we keeping the probe on for like 3?
Yeah, I think so. But I don't think we will do any more heat flow measurements unless something like really important, and like they discover something, and then I think we will assist Babe or Z with doing these things.
Yeah.
But fish, yeah. I mean, it's complete dark there, right? So I don't see the point of the eyes. Okay, for those fish lovers, we have a visitor, and they kind of tend to stay along and probably attracted by the light. And I love when you can get to see them close to the camera. They're beautiful. Oh, there's 2 of them actually. Oops. No importa que estemos en la falla, valdría la pena. Pero no la va a ser completa, ¿no? Es que nada más de gradiente. Pues sí, bueno, yo decía por estar encima de la falla, pero
Okay, probe out, please. And we move 25 meters.
25?
Yes.
Got it.
Thank you.
so we're not doing a complete measurement here. We're just gonna infer the thermal conductivity from the previous station, and then we're gonna move 25 meters on the same transect towards the vent field. Entonces en esta ocasión no hicimos una medición completa, vamos a inferir la conductividad térmica de la estación anterior y vamos a movernos un poquito más cerquita, a solo 25 metros de lo que creemos que es este escarpe de falla, y comparar las mediciones.
ROV bridge. Yeah, go ahead, Luke. Hey, you gonna want us to hold position at this waypoint?
Yeah, just hang out there for a minute. We're doing smaller moves right now, so
Okay,
thanks.
will do. Thanks.
Can you see that?
Yep, rubbed on.
Okay.
Just a second, just get
Just a second, it's not, wait,
Okay.
it's not stable.
Yeah, all good.
Okay.
Stand by, stand by. This came up, yeah, so just grab that one there.
Yeah. Did you move?
Yeah,
Yeah, they moved.
sorry.
Sorry. You wanna, it's okay, no?
Yeah, we have a few seconds before the incident go.
Okay.
Okay, I think we're good.
Okay, as long as we see the probe, yeah, it's fine. We'll be fine. It's a few seconds.
¿Sí? Sí, sí alcanzamos. Sí está clearing. ¿Qué pasa? Sí, está bien. Yo ahí les hablo. Ok, gracias. Ya está, pero... ¿No? Okay, listo. Can you insert the probe, please?
Okay, ready to probe?
Yeah.
Up and down. You okay with the view there?
Yeah, that's fine. It was fine. So you're inserting the probe.
Okay, that's all the way down.
Yeah, you're good. You're good.
Yellow's the very
you.
top there, mister?
Yes. So as long as it doesn't remain flat after the first peak,
Means it's getting green.
yeah, it means it's getting big. So we're good.
Count.
Yes.
What were the first two?
1.5 and 1.7.
Okay.
So
So our background is lower than what we saw before.
yeah, it's a little bit, but we're farther away though.
Yeah, yeah.
So,
But even at Alca, we were at 2.2 in the background at Alca.
Right.
As far away as we got.
right.
Okay.
Yeah. So
It's pretty simple. Yeah.
we're gonna be moving 25 meters for the next one as well. And we're gonna stay a little bit longer here because we're gonna do the whole measurement. So we're gonna wait for the spike, the second spike, and then 7 more minutes to decay.
So
So
the spike is just a huge resistor that just creates a bunch of heat really quickly.
that's correct. So it has a heating wire, and so it creates a pulse that goes to all the misters, and then we see how fast they decay. And so depending on the properties of the sediment, it will vary, right? And so then we take that information and you get the thermal gradient, you get the thermal conductivity and other thermal properties of the sediment, and then we use a MATLAB for an inversion, and that's how we get the heat flow.
Well, how do you decide which, when you're doing the probes, when to send that?
When to send that?
Yeah.
It's actually programmed by in the
But do you do it every time we go on, or?
no, not every time. I mean, sending the pulse.
Yeah.
That means a full measurement. So
Okay.
that's when we send the pulse, and but for some, when there's no big variation between stations, you can save those minutes.
Okay.
And so you do a half measurement. So it means that you only take the thermal gradient
Okay.
out of the
Without
measurement.
that spike.
Yeah.
Okay.
And you infer the thermal conductivity from the previous, saying, well, we are betting for the thermal conductivity remain the same,
Okay.
and it's shorter, right?
Yeah.
But in this case, we had a difference of about 200 milliwatts in just short distance, so it's not insignificant. So that's why we're measuring the whole thing right now. So nice.
Yeah. That's awesome.
They're so beautiful.
That's better.
So we fire the heat pulse now, and we will wait for another 7 minutes or so until the measurement is complete, while we are admiring this beauty, even though it's a little blurry right now, but it's just beautiful. En la mañanera. Ay, bueno. Me hiciste reír.
es una serie de químicos de alcohol. Necesitamos pones alcohol, se tritura y entonces así te vas hasta tenerlo más puro. Porque haces unas pruebas, entonces hacen unas pruebas, se corren unos geles, se llama gel de actinamida. Entonces es un gel donde tú pones micras de unas gotitas de todo esto y corre eso como un corte. Entonces cuando corre y pues muestras, puedes ver cómo se separan las moléculas por pesos. Es como conocemos cuál es el peso de las moléculas del ADN, si tienes bandas en ese peso, es que sí extraíste el ADN. Entonces ya ahí apenas sabes porque extrajiste el ADN. Dices, aquí el ADN, ahora quiero mucho ADN para secuenciar, para identificar cuáles son las réplicas que tiene el ADN. Lo metes en otro aparato, que es la PCR. Lo metes en PCR para que multipliques todo el ADN que tienes, porque lo que quieres hacer es secuenciar el mayor detalle de todos los datos. Necesitas muchas cosas. Entonces, después de que haces tu PCR, te dejan alrededor de media hora, porque lo que haces es insertas una enzima que esté duplicando el ADN. Entonces, esa enzima hace muchas cosas. Toda la máquina tú le tienes que solucionar el problema. Tengo esta letra, tengo esta letra, tengo esta letra, y lo que hace la enzima es decir, tengo una letra muerde, pues aquí tengo la, pues aquí tiene que ir esta letra, va poniendo, entonces así obtienes tu secuencia, y después de eso lo tienes que mandar a un laboratorio a que lea tu secuencia, y eso se hace a través de aquí hay un formato, no sé, por colores, porque toda la tiene diferentes colores, entonces de acuerdo por los colores que dan, ya empiezas a armar tu secuencia. Entonces, ya lo que te dan al final es la secuencia de letritas de todo eso. Y ese ya es lo que metes en la computadora. O sea, en la computadora tienes que limpiar todos los datos porque hay cosas que metes artificiales para que tú le digas a la enzima que te pongas aquí, quiero que hagas esto, entonces eso es lo que limpiar todo el ruido del aparato y luego ya hacer los análisis.
Okay, ready to roll out, please.
So Prof coming off the sediment, and so we're finished with this measurement, and we will move another 25 meters
Halloween is 31 and Día de Todos los Santos. First, November 1st.
to do the next station.
October. No.
It's fine.
Okay.
Never mind, don't put that.
Yeah, we're way faster.
I
Well, technically we do.
Cuando se hacen los humanos, puede ser
Sí, hay un creo que, por ejemplo, bueno, yo lo conozco con tiburón.
¿Lo recibe?
One second.
Okay.
That's fun. It's good.
Okay, roll into the sediment, please.
Okay, coming down. All right, we'll stop.
Thank you. So
Empezaron a sacar
basically, sí.
serán nada más 25 metros, ¿no?
Aquí pues ahorita vamos a pedir que vamos a tomar esto a partir de ahora. Sí.
1.65.
They wanted to go to 3,000. Yeah, like no, I mean, yeah, like yeah, about halfway. Like this field when you watch it on here. And then they want to go to and then yeah, like the
Entonces el otro a lo mejor está sobreestimado, ¿no? Un poquito. El anterior podía haber estado sobreestimado porque es más alto que este.
Pues es que es la cara, ¿no? Entonces si ahorita estamos nosotros 50, si esto es 1.5, entonces está simétrico. Porque fuimos 50 primero, fueron 1.5, sobre la falla 1.7, sobre 25, 1.65 y ahorita somos 50, entonces si estamos 1.5 entonces está
Sí.
the ship's having a hard time making a round loop, so you may want to move him down nice and slow just so he's a little bit heady and like just not far enough that he's gonna
Va a ser thermal gradient solamente.
I just figured just get
Sí.
single government.
See?
So guys are gonna say.
Okay.
I'm gonna keep it on. It's in between parallel and irons. How far is the next move?
We're still deciding.
Still deciding, okay.
Yes, I'll let you know.
Thank you. Okay.
Estamos a... ¿Cuánto? 550.
White box too.
Say no?
The next one is going to be 100 meters, please.
Yeah, now we're making progress.
Okay, so we're gonna have a short measurement here, and we're just gonna go and for the thermal gradient, and we will be moving another 100 meters towards the band field for the next station. So what was interesting in this particular tree station is that we were crossing a fault, and so we wanted to observe what were the difference, west and east to the fault and on the fault. And so we are getting interesting results that are the particular relevance when you're trying to understand the thermal system of hydrothermal band fields. So now we will be moving a little bit faster in terms of distance. So if you have any questions, let me know.
Okay, get the probe out, please, of the seabed.
Where is ROV?
Probe out?
It's out.
Okay.
ROV bridge.
Yeah, we have a new waypoint for you.
Updated waypoint. Thank you.
Thank you.
Muy bien, nos estamos moviendo entonces a la siguiente estación, que va a estar 100 metros en dirección del campo de ventilas hidrotermales. Y hace ratito estaba explicando en inglés que estas 3 estaciones que hicimos son particularmente importantes para nosotros porque cruzamos el escarpe de una falla. Entonces explicaba que es interesante ver si hay variaciones a los lados de la falla y sobre la falla, porque esto nos da información para entender cuál es el rol de las fallas en este sistema de ventilas hidrotermales, es decir, cómo funciona la plomería básicamente del campo, aun y cuando estamos a 450 metros del campo. Es interesante ver si en medio vamos a encontrar variaciones o si el gradiente de temperatura, el flujo de calor, perdón, va a ir subiendo suavemente o va a haber incrementos sustanciales en poca distancia. Entonces de eso se trata el transecto. Si alguien tiene una pregunta, avíseme.
Sí, hay preguntas, ¿no?
Mande, sí. Thank you, John. So now you get to see a picture of the bathymetry of where we are and how we are moving, and so the three-dimensional adds a perspective, right? And so it's not that we are moving just across the seabed, and so you can look at the the most important topographic features. Pues no, Florian, serían 325, ¿no? Si nos movimos, si estábamos en 425, nos movimos 100 metros.
No estamos en 425, estamos en 450.
A ver, la primera la hicimos a 550. Es que es lo que hay que contestar, Rafael.
55.
Entonces fueron 550, 500, espérame, 400 ¿qué? 70. A ver, entonces es 550, 500, 475. .7. Chale.
Yes. There's a CTV.
No. Aclararle las distancias a Juan. Primero 550, luego nos movimos 50 metros, estábamos sobre la falla, estaba a 500.
Sí.
luego le ponemos 25 metros,
Y luego otra vez.
luego otros 25.
Y luego ahorita vamos a hacer.
¿Seguro que no fueron 50?
No,
Fueron 12 a 25.
sí.
Entonces, 475, luego 450 y luego 350.
Ahí está.
1.7. Ah, perdón, sí.
¿Ahora sí ve?
Yeah. I'm still moving.
No, they're still moving. ¿Cómo lo interpretas?
Yeah. All right, we're on mode.
Okay.
Okay. It's probe zone, right?
Probe's on, correct?
Yeah.
We have
Yeah. We will wait until.
How's it going? How many stations have you got?
It's good.
So if you want to look at, so we're doing this last one. with this have happened. So 1,500 meters away from the vent field, west from the fault, east from the fault, and another 25 meters away. So we thought we were going to look at what it looked like a nice anomaly. But then we got this last measurement, went back to 1.7.
okay.
So it's messing with my with my curve.
Yeah, the too much data problem.
So we're gonna take this one. So we moved 100 meters from the last one.
Okay.
I think we're gonna be around heat flow, the background heat flow around. I would expect to be
Probe into the seabed here.
higher.
So on the east side, it was what? I'm forgetting.
1.5.
It was?
On the fault, it was 1.7.
Right,
And
but
that's-
yesterday on all the way on the ends
On
the other one.
on the last. Let me see. I think there's graphs
Okay,
somewhere.
All the way to
So the red one is the red slug log. I don't remember, but it was. So this is the first day. Yesterday, today we started around here, so I guess it was lower. I don't have the log, but so and that's the black spots are AUCA measurements, how they pay.
Oh, okay.
So
And this is not showing the. Oh, this is a log scale.
yeah, it's a log scale.
Okay.
Did we get the yellow one on that? I haven't seen the yellow one. Wasn't.
Oh yeah.
Is it good?
It's good. It's not the didn't get a lot of friction on it, but that's okay.
Okay.
As long as it's registering.
Perfect.
Yeah, I guess. So.
Okay. Do you all need help cycling through lunch, or?
No, I
Yeah.
don't. I will not take that.
Okay.
That's okay for me. No, yeah, my real break will be at the preparing the science.
Okay.
Yeah. All right. Thank you.
Yeah.
So we're going to start together and visibility.
No. No subió mucho, pero sí está registrando, ¿no? El amarillo.
Sí. Muy bien.
How far? It will depend on the value that we get from this last one. I'll let you know in a minute.
So stop asking.
What?
I will stop asking because it depends on the value. I thought you had a preset 400.
Well, you know, if it's we were kind of away from the bed, farther away from the bend field, and then we crossed a fault, and we wanted to see what was going on with the fault.
50 meters.
That's 50 meters then.
Thanks, Chloe.
Esa sí va a ser completa, yo creo, ¿no? Well, sorry for the low visibility, but what's going on is we are
Bridge.
in our fifth station.
Hey, Ben, are you going to want us to stop at this upcoming waypoint?
Roger that.
All right, I'll stop and be handing over to Tiago soon, so he'll be on comms for the next 4 hours.
Roger, thank you.
Thanks.
Sorry, I was just saying that. So we are in our fifth heat flow station along a transect that goes east-west, and so we'll be started today the farthest point from the vent field, and so if you hang in there, you will get to see the chimneys when we get closer to the vent field. But for now, we're just performing the full measurement for this station. And so we are 350 meters away from the vent field, and our next station will be 50 meters away. So if you have any questions, don't be shy, let me know. And welcome, Jazz. It's great to see you.
Road Bridge.
Yeah, go ahead.
So you updated my waypoint?
Yes, I did.
Okay, I'll head there. Thanks.
Okay, so we just fired the heat pulse, and as you can see on the graph, it's the second big spike on the graph, and so we will have to wait around 7 minutes to see how the thermistors decay in terms of temperature. And so we will have information not only on the temperature gradient, but also on the thermal conductivity and other thermal properties of the sediment. So after that, we will use this data to calculate the heat flow in each station. No hubiéramos ido 100 metros, bueno, atendiendo la temperatura más rosa. No me hubiera movido 100 metros en lugar de 50, pero ¿cuánto crees que sea esto?
Solo 100 metros.
¿Eh?
Como 100.
Sí, pero dijiste que para las siguientes 50.
Sí.
Yo me hubiera movido otros 100.
¿Otros 100?
Yo creo.
¿Qué lo que dicen?
Sí, el Rob dijo que ok, pero
No, pues ahorita pues esto no es así, pues van a ser similar.
ahorita
Va a ser igual.
va a ser igual.
Sí, parecido. Muy parecido a los otros. Entonces tal vez hay que ser menos 100, ¿no? Ya para el amigo ese. Pero igual dijo que quiere unos entre el campo y la falla.
ROV bridge. Go ahead, bridge. Alright, are you gonna want us to hold position at this waypoint?
Yeah, we still have to move the next one, so we'll hold position here. Move you when we get going again.
Alright, thanks.
Thank you.
Bye.
Okay, probe out of the seabed, please.
Okay, with the measurements done, so we're pulling the probe out of the sediment now, and now we will process the data and let you know the heat flow value if somebody is interested.
Thank you.
Move to the next location?
Yes, we said 50 meters. Can we do 100 meters? Please?
Bridge, ROV.
ROV bridge.
And they actually were moving further than the top, and I'll just keep going, I'll move the waypoint.
Alright, I'll bring my heading background starboard then so we can get the move.
Roger.
Thanks.
Gracias.
Sorry for the correction, but yeah. So it's always nice to check what's coming on. If it's too similar and we still have to do a lot,
I
then
understand, yeah.
it really doesn't make much sense to do it this close. poquito de hit de media hora. Pero está padre.
Ah, bueno, sí, ahí en el
Ayer lo hice y eso que había corrido en la mañana. Tuvimos tiempo de esas mañanas dicen más que ahora me duele el hombro, que ya no me había dolido. Sí. Pero entonces se cuenta que está padre porque también te rex.
Ah, sí, sí. Sí, así antes de hacer los ciclos en el cambio de repente también.
So if you're looking right now, then you have this view of the bathymetry map and 3D, and so you can get a sense of how far away we still are from the vent fields. But it's really important for heat flow measurements to be systematic, and even though we could go faster, you know, larger spacing between stations, it's always important to be thorough. Si están viendo la imagen ahorita en la batimetría en 3 dimensiones, se pueden dar una idea de qué tan lejos estamos de los campos de ventilas hidrotermales. Va a ser alrededor de unos 250 metros más o menos. Estamos en camino hacia la siguiente estación. Pero bueno, la vista de la batimetría en 3D siempre nos da muy buena perspectiva de la distancia y de los recorridos y del tamaño del vehículo con respecto al campo.
So it seems like we're getting more clams and gallopers as we get closer. Is that you're seeing that?
Yes, yes.
Yeah.
Actually, was going to tell the audience that we're seeing a lot of clam
Okay.
traces.
That's what I thought I was seeing. Yeah, see, those are live because they've got the siphons coming out.
Right.
But those anemones, see, those are anemones that grow on the clams. Mm-hmm. Let the clams take them around.
So they're in for the ride, huh?
We call them clam handles. So
Clam
you run a
handles.
sample of clam, you grab the anemone.
Oh, nice, cool.
Ron, see that?
Okay,
Roxanne. So getting ready to insert the probe, and you might have noticed that along our transit that there are much more signs of clams, paths or traces, and you also see like siphons that are attached to the clams for the ride. So as we move closer to the vent field, then we can start to see much more interesting ecology. Ok, no sé si notaron las trazas o los caminitos que dejan las almejas al moverse. Ahora se nota mucho más que la ecología está mucho más variada y presente conforme nos vamos acercando al campo. Entonces esas trazas que se ven en el sedimento son las huellas de las almejas. Y los sifones que se ven que están como pegados a las almejas, en realidad están ahí, se pegan a las almejas y se transportan con ellas.
Okay, is there pearl, please?
¿A cuántos estamos del campo? 250. ¿A cuánto estamos del campo? 250.
250, sí.
You want to play?
No, do you want to tell them why the clams cruise around?
Tell them, please. I have to take a break. And I'm very bad at the camera. I cannot zoom in right now.
Good afternoon, everyone. This is Z. Just had a great lunch on the Falcor. Food here is so good. So the clams do make the trails. You can see the clams at the end of the trail. So why do the clams cruise around? Some of the clams here, like these big ones. Now, before I say this,
when the biologists come on, they're probably going to tell you everything I said is wrong. But as a geochemist, my understanding is that as these clams cruise around, these clams do have symbionts in them. As they cruise through the mud, their foot is underneath them, and their siphon is sticking out. You saw those white siphons, so they're sucking in seawater, but they can also absorb nutrients through their foot. And there's a little bit of sulfide in the sediments, not necessarily from the hydrothermal fluids, but from decay of organic matter and sulfate reduction. And so these clams have symbionts that can metabolize H2S. And so they cruise around and they pull in sulfide from the reducing non-oxygenated sediments underneath them, and they bring in oxygenated seawater above. They bring those two things to the symbionts, and the symbionts can then burn the hydrogen sulfide with the oxygen and use those for energy. Now, there are clams that also do the same thing with methane oxidizing symbionts. And on the next leg, we'll have biologists. There's at least 3 species of clams here, if I'm right. I don't know if any of them have methane symbionts. But it wouldn't be unexpected, especially around the vents, because these vent fluids do have a bit of methane. So that is why the clams are cruising around. And we're away from the vents here, so you see they're looking around for a little bit of sulfide. You might notice that when we get in toward the vents, the cold seeps, and there's just clams everywhere. They don't move because now this hydrothermal fluid is bringing sulfide to them. And we got a little bit of a snowstorm here, but I think I see a picnic on it, but it could be an isopod out there. We'll go see if we can get a picture of him or her. A lot of sushi in the water today makes it hard to do camera work. Some of this is from our thrusters, but even I've noticed through the dive there's just a lot of cloudiness. So a lot of sushi in the water. Let's wait things clear up and we'll see if we can find that little critter, if he's still out there. Yeah, let's look at the clams while we're sitting here. Okay, and so there you see the pink things are the siphons of the clams. But you also see there are anemones, the bigger white anemones. They like to hitch themselves onto a clam, and then as the clam stirs up the mud, they're getting the benefit of that. So they ride along with the clam. So the pink things coming up out of the sediment are the clam siphons. The white with the pink or the purplish are anemones that just use the clams as a way to, they want to be on a hard substrate, but there's no rocks here, so they attach to the clams, and then the clams help them. Oh, you just saw a siphon go in from one of the clams there. And so they are filter feeders, but as the clams burrow through the sediment, they stir things up and they get a little bit of nutrients from them. So the pilots, when sometimes we have them collect the clams, and it's kind of hard to grab a clam without squishing it, and that's kind of ugly. But the anemones serve a nice function. We refer to those as clam handles. And then for reasons known only to itself, there's a holothurian that decided to crawl up onto that clam. And look at all the bacterial mat coming off of that clam. Okay, and again, he's got an anemone on him, but right there is the siphon of another clam that's buried in the sediment. And again, there's another siphon. There would be a clam buried underneath there. Who else is out here? Oh, there's I think this is going to turn out to be one of those isopods, but we'll see if he's a pycnogonid or an isopod. That looks like an isopod. and I'll get this wrong again, something like Munopsidiae, if someone, I think that was Lisa who said that was what these are.
Okay, go out of the seabed, please.
So I'm a little confused about Lisa's on here all the time as the unknown explorer. Everybody knows she's Lisa. Who does she think she's fooling with, this unknown explorer? I don't know. We all know her. There's a little shrimp.
Okay. Yeah, move on.
Is that where you want the camera? Okay. And we're going to move to the next station now. Someone asked if scallops can live this depth. I have no idea, but I've certainly never seen one that deep. You got to save these questions for leg 3. We have people who can actually answer questions like that.
Estamos en la de, vamos a hacer la de 50.
No, that's a
All right, we're on seabed. Ropes on.
Thank you. ¿Sabes si esta noche tiene una de estas? Tiene una de estas.
No es una de esas.
¿Seguro? La alguien.
Sí. No. Y además ahí saben también, supone que los propios técnicos tienen el software.
¿A qué averiguar esto?
Sí, pues esas ellos las hacen.
El software no. El software
Ah, bueno.
es el software es
Sí, bueno, pero el interfaz, quiero decir.
Ah, el interfaz sí lo tengo. El software también tengo.
Sí, hay que preguntarle.
Hay que estar muy claro eso, porque si no está en esa cosa, lo único es esto, eso es
Sí.
Vamos para estar muy claro. Y le hicieron un fitting al backward, $60 millones este año. Ahí está valiendo cuestiones de internet y eso.
¿Sí?
Sí.
Wow, te va a tocar un modelado.
Sí, porque tenía miedo de que yo si no tengo internet no puedo hacer. Okay, probe in the seabed, please.
Okay, so we're ready to insert the probe after the equilibration of thermistors. So we're 200 meters away from the bend field, and now we're start to move in a space with a spacing of 50 meters. And then when we are real close to the bend field, we might close that gap.
It's good.
It's good. Thank you.
Yeah, we started.
Okay. So guys, let's remove out the probe. Have sediments in the probe, maybe on the flat.
Okay.
Up and down.
Yeah. Side to side as well.
Yeah, something to get off the sediment.
Do you need that now or the next one?
No, not right now. No, it's in the sediment. But when it gets out and you see the sediment, maybe I don't know. You can maybe up and down or something like remove it.
We can move the other way.
Thank you. How are you doing?
Ben, do you need anything? I'm good, thanks. Anything to drink? Okay.
Just lay it off, yeah. Go ahead and work it out. Just look zigzag.
Give a shout out to my friend Karen, who's from Davis, where I'm from. Nice to have you watching us, even though what you're watching is a bunch of muddy TV at the moment, but that's life in the deep sea. It'll clear up. Let's get a glamour shot for Noonie if Noonie's on. I don't know. But I know he loves his fishies. So that's a zoarcid, I believe, and they tend to hang out at the vents a lot. Although at this site, we see them out here in the sediment more than usually if we're on sort of basaltic substrate, volcanic substrate, they really hang out next to the vents. Out here in the sediments, we see them away from the vents more. And there's another monopsid. And somebody will correct me if I'm wrong, which is an isopod. It's really trucking along.
There's something bigger coming in from the left. See? Something off to the left. Looks like a big uniform. Going to the left. Right there.
Ooh, who have we got here? Something gelatinous and ugly. That looks like a ctenophore. Let's see if he'll give us a light show here. Oops. Oh, there we go. Now we're going to get a little bit of a light show, I hope. The light bounces off their ciliates on the little fiber things, and they get these beautiful flashes of light sometimes. This one, we're not seeing it quite as much as some of the other ones. But look at the delicate patterning of him. He's a very attractive critter. Well, I'm going to lose him, I'm afraid. Yeah, he's camera shy. There's all our little white anemones that hang out in the sediment. They're very common around here. We see lots of those. I don't know who that stick is or was. He doesn't look very healthy anymore if he was alive. But it looks like somebody maybe, looks like little amphipods maybe on him. Little white guys. Not sure. Yeah, there's some little white critters on there eating the bacteria. And what is that? Is that a little tiny ctenophore? Not sure I can focus on that little purple dot. Now, the camera wants to focus on the background. Let's see if we can fix that. Oops. Gently now. You can all have your guesses of that because they're going to be just as good or better than my guess. I don't know what that little thing is. There's a purple anemone. And the camera likes the sushi better than the anemone, so we're going to look somewhere else. I'm going to call that a jelly. Okay, I heard it's a medusa. I don't know why the jelly is sitting on the seafloor. Maybe there's some peanut butter under there. I don't know. Not really.
How far are y'all gonna wanna go to the next one?
50 meters, please.
5-0?
Yes, I see. Oh, you're fine, you're fine. Stay there.
Okay, so go ahead.
A las 2. Sí, ya lo vi desde la mañana.
Your jelly took off. Okay, oh no, then.
Yeah, so, like JaichMaa is from Bahrain, and he's a jelly expert, I think. And he identified that on the chat. Might give George a shout out.
Clam crabs.
Okay, roll on of the seabed, please.
Just finishing the measurement and retrieving the probe of the sediment. Next station, 50 meters towards the vent fields. So we will see what waits for us there.
And we'll clean it off this time.
Ready?
Yeah.
Just gonna fly around a little bit. Exactly.
It's fine. Perfect. Perfect.
A little slow. How far up on the bottom mark? How far up on the mark?
Keep going.
Sorry, we'll bring it down, don't come down any lower. Go over to your forward.
Go left.
Actually, I think we could thrust backwards. That's plenty even. Right. Over here, that's, are you happy with that? Are you happy with how clean that is?
Yes, thank you.
Yeah, that's perfect. Thank you, Jay.
Now, I'll make
It's shiny again. ¿Qué querías que viera el...? Ah. El alien. Bueno, como pueden ver en el mapa batimétrico, nos estamos moviendo hacia la siguiente estación, solo a 50 metros de la anterior. Y esto es porque conforme nos acercamos al campo, estamos esperando que las mediciones suban un poquito y necesitamos tener una mayor resolución. Saludos de vuelta, Alex, desde el Falcor.
Okay. Wanna see that?
Roger that.
Here.
Don't sound right.
Yes. Thank you. Okay, probe into the seabed, please.
Roger that.
Thank you.
So probe it's going in again for this station. Let's see if every thermistor gets in. Hopefully they will. Bien, buena predicción, 2.71.
Looks good. Thanks.
Looks good, yes, thank you. Sí, son desde el primer día, ¿no? Desde el primer día al este.
Que le bajen el cool.
¿Mande?
Que le bajen el cool. Que se confunde. closer to that land.
Que siempre con competitividad.
Okay, get the probe on, please.
Okay, so we're cutting the measurement short because we're gonna just deal with the gradient, the thermal gradient for this one, and assume the thermal conductivity and continue moving towards the bent field. Okay, en esta medición terminamos la medición un poco antes. So another 50 meters, please. Yeah, just let's double check, but yeah. Yeah, it's another 50 meters, please. perdón por la interrupción. Les decía que terminamos esta medición sin tomar la completa, porque vamos a asumir que la conductividad térmica no varía mucho, con espaciamientos pequeños de 50 metros, eso suele ser el caso. Y vamos a continuar moviéndonos hacia el campo de ventilas hidrotermales. Para recordarles nada más, la profundidad actual, estamos a 3.680 metros por debajo del nivel del mar.
Pretty likely to be in a bunch of tailors in this next site, so you might have to search around for a good place.
Okay. Thanks for notice.
And if it's really blocky, I think what we do is just go perpendicular to the line to the southwest. And that'll get you in the mud closest to the line.
Okay.
Because if you go either up or back the line, you're still going to be in that tail site.
Okay.
So, yeah, we'll see when we get there, but it might be tricky.
Okay. Sure.
I would probably be the pro.
Yeah, for sure. Do you know the height of the chimneys? Maybe how many meters tall?
This one, I don't remember exactly. This one is probably, I think the short one is on the order of 10 to like 12 to 15. The other one's about 15 to 20.
Okay.
Like that.
Okay.
And they're smaller than the big one, but not long.
Okay.
That's pretty close.
So yeah, during the time that the inset with the 3D bathymetric image was there, Barbara is asking if the formations, the chimneys, the edifices as such are 50 meters tall. The answer is no, not that long, not that height. Is the small one is around 10 meters, and then the middle one is around 10 to 15, and the other one is the highest, probably around 25 meters or so. Still big though.
See on the sonar that you've got a lot of hard scatter. Mm-hmm. The scale is 50 meters.
Okay.
above the ground?
Yes, please.
Before you lay it down.
You willing to collect a rock sample? That's a little chimney. And this would be a good place for a Ron's push core as well.
Yeah, keep the torch on.
Depends on your schedule.
Yeah, sure. Sure. I think we're gonna do a push core for Ronald here, so that could be a good coping. I might go for a push core here. So if you want to do the push core as a coping test, that's fine. Or,
I'll get this out right now. Just for-
sure. Yeah. So since we are so close to the vent field now, we're going to have to be careful where to insert the probe. So the pilots are going to poke the sediment just to make sure that we don't hit anything hard and that the probe is safe. It's normal to have outcrops and pieces of calcium that are scattered in the seabed. So we need to make sure it's a safe place.
Before you lay down, just rack out that whole part. Ready to get? I can do it if you want to, but you've only got 15 meters through it.
Push core. Pero
Isabela, ¿lista para el...?
Sí, estoy cuidando también. ¿Cuál es el?
Ahorita te digo, es que no alcanzo a ver.
What's that? Right, that-
Es la E, ¿no? No.
Is that A on that one?
A.
Oh, so that comes out.
Ah,
Yeah, that's A.
that's A, right?
Yep.
Es A.
We can't really see that chimney right now. What are we, about a meter and a half, I think?
From the what? From the chimney?
Yeah, I want to describe where the core is for rock.
Well, maybe we'll have to add that later when we can.
Yeah.
I don't see it on the other
I
cameras.
mean, yeah, no, I have no idea, but just based on we should be pretty close to the chimney.
No, I mean, there was a little hydrothermal chimney that we came in.
Oh.
That's what I asked if we could rock sample.
Okay.
And that's why he wanted one next to an inactive site. That's why I thought we'd take the push program. But it's off the screen, it's over there. What I want to do is, once they've got this, let's pan the camera over so we can see how close it is, so I can describe how far away it is from the chimney. So this is what's going to be one of its inactive sites.
Okay. Perfect.
Is it core two,
So it's core.
number 2, right?
Yeah, you did one core this morning, yes? Background
Yes.
core. So this will be core 2, but it's in 2A.
So in additional text or notes, you want to write any notes, please?
Yeah, we may have to edit it because I can't see it. So I want to say about 1.5 to 2 meters. Okay. From an extinct height. All right, did you take this one?
Yes. Please.
But once we pan the camera over there, I might want to change the distance. You can't see it right now. But that's still good.
Just the one, right?
Just the one, yes. Okay. You wanna take a look for the rock sample?
Let's do the measurement first because
Yeah.
if we go over there, we'll screw up sediment.
Right. Right.
And my advice would be, again, we'll go park next to it. It should be a really quick, easy grab unless it's really fragile. And if we grab it and get fragments, forget it.
Okay.
So it's either it's going to be an easy sample or we don't do it.
Okay.
Y'all ready for heat flow? You want me to
Yeah.
stand the ground?
Yeah. I need Florian to start the. But yeah, just
You
give
want
me
to
a
stand the
minute.
ground while we're here?
Oh, you go over here?
Yeah.
Follow me.
Well, just wait until.
Not in the library.
I got a hard bottom.
I'll check in that.
Oh,
yeah.
did you?
Yeah.
Oh,
About
good.
that deep in.
That doesn't surprise me.
Yeah. Okay.
I only made it that deep in before I got
Me estás poniendo nerviosa.
that deep before I hit bottom.
Yeah, so shall we move a little bit?
Here, let me just move it.
Yeah, try
Make sure it's not one rock.
Because it could just be a clam or
Right.
a rock.
Now lift up the ROV.
Yeah. Está duro.
What do you want to do? Do you want to try to go forward or backwards, or which direction would you like us to attempt to go?
No, a little bit forward then would be.
Let me bring down.
Or there's a, we want to come back, there's a hydrothermal chimney that just up the left. We want to come back, I understand, we can find a good place to do it. Okay.
Y eso lo reportas como un sitio nuevo, ¿verdad?
Yo no empecé de nuevo.
Entonces puedes ir por un sitio nuevo.
Hacer el sitio de edifices.
Yes, I am a child and I know it. What kind of samples are you talking about at that event? Water samples?
No, just grab the chimney. But if it's really fragile and fractures, forget it. If it's an easy grab, we'll go for it. Because it may be too fragile to grab, and I don't want to waste a lot of time. It's not going to be able to do that. But if it holds together, it will take the
Can I
time.
put my sword through it and see if I can
Skewer it.
skewer it?
Yeah, that would be good.
Just come on.
Before you lay it all the way out there, I'm just gonna stand it up. I'm still hitting bottom about that deep. And so I got deeper here,
Uh-huh.
but not, I mean, that's significantly deeper. It's up to you on what you want. All right.
Okay.
I think if you want to get a sample, you got to move perpendicular to the line
Uh-huh.
to get further from the vent, or else you're probably going to hit our substrate. If you go along or back the line is what I'm guessing.
Okay.
You want to get down this way.
So if you want to just move like
Directly.
5 meters perpendicular,
From that,
yeah,
Yeah. Let's see if we can get a
yeah, right about where your cursor is. That way, it's almost still on the line, but you got a better chance of getting penetration. I think. That time good you would go.
yeah.
Okay.
Sounds makes sense. Thank you, Zee. So as you can see, we're having a hard time finding a safe place to insert the probe. So we are gonna move perpendicular to our transect line, not too far from it, but just to try and see if we can find a softer place and it's secure for the probe to be inserted.
And, given that we got some hard stuff here, even if you get a measurement, I think you should do it on heat pulse here too. Thermal conductivity
Oh,
could
yeah, yeah.
slightly be different.
We will.
Okay.
We will definitely.
Just check it.
Yes. Excalibur. Ooh. Oh my god.
this sword is in a stone.
Okay, which way do you want to go, Z?
Oh my gosh. Did you see that, Z?
Same way.
I would drive another 5 meters in the same direction on that. Then it's your call.
Just move and try. If not, we pass the chimney and then start going eastward. Yeah.
Actually, if you look at the topography, look at the topography.
Right.
If we do go ahead, there's that little imprint. You might have a better chance in there.
That's also true.
But I think you're better off being further from the chimney to try and get a measurement. But I don't, it's a guess.
Okay. Let's see. Yeah, baby.
Okay, this
Good.
one here.
Good. Oh, you're mean.
Oh, you got the seabed?
Almost. Settled down. Let's go.
Roger that. On seabed.
Okay.
Probes on?
Is probe on?
The what?
Probe.
Yeah, we never turned it off.
Ah,
Okay, good,
Yeah, we
perfect.
never turned it off. Yeah, it's still on.
Okay, so finally we found a soft enough place to insert the probe, and so we're going to proceed with a complete measurement here. And since we're finding a different composition on the seafloor, we will make the full measurements to measure the thermal conductivity here as well.
Cody, who do you think's flying?
You can see.
Hmm?
You can see.
Can't see.
Is it?
Estamos a 100 metros de la...
Hi, Cody. Is the baby home?
We miss you.
Let's go.
Bueno, la original, en la posición original estaría
Okay, let's
insert
get
the
the
probe.
probe inside the sediment. Okay.
So we're inserting the probe.
No, okay, stop. Go down.
Bring you back up.
You're gonna leave the spike in and move over to that area?
Bring it all the way back up. before
Yeah,
you-
sure. Please.
You're gonna put the spike in where we know we can get in all the way?
Yeah.
And then
Yeah.
do that spike?
Yes, please.
Pero eso ya va a ser en
What's that? I'll go right there. You're gonna shoot the area right here, then. I'll leave that there, and,
We can keep it safe.
yeah, it's a little tough, but
You should be out of this week now.
no, but it makes it easier for you. Just get to that area.
The spike is the same longitude as the
It's a little bit
probe.
longer.
A little bit longer. Like how long? Do you know exactly? Like 70 centimeters or?
Yeah, I think counting the handle and everything, I think I have to make everything 75 and then the handle. So
Okay, good. Thank you.
Don't go too high, just for that. See it right there. You don't have light, right?
So as you saw, we didn't successfully inserted the probe. And this is normal because we are very close to the vents. And so it gets trickier for us to insert the probe in the right place so it doesn't bend. So now we poke twice, and we're pretty sure that the spike, which is a little bit longer than the probe itself, went all the way through, and so hopefully we'll be successful in inserting the probe this time.
When they're ready for it. You wanna go in with it now? Or do y'all need to do another?
No, I have to start the measurement before.
Okay.
Yeah, just give me a second. So for the people who were asking how far from the vents we are, there you have the bathymetry 3D image. And so it will appear that we're not that close yet, but the sediment is different. It's definitely different than we observed in the more distal parts of the basin.
Okay.
Okay, we're ready. Please. So here we go again, trying to insert the probe. It's looking better this time. Oh, come on, come on, come on, come on. Yeah.
Nice. Very nice.
Sweet. Thank you.
you ready?
See, we're going see after this. We're going to the gymnasium.
I'd like to do the desert.
So how far are you away from the field? About 50 meters.
It's
Those are 10 meter squares. Still, yes.
What's that?
We're on still 10 meter squares.
No, those are,
No, we're
those are 100. And I'm over here on 10 right now.
Okay.
So 50 meters, something.
I can zoom out a little.
Yeah, but there's, you see
It's
there's,
just like over here somewhere.
yeah, but you see these little bumps, those are old hydrothermal mounds. Yeah,
Oh, okay.
So,
Yeah, I think it was over here somewhere.
yeah.
Here we go.
Good, we're in some hard ground. So we
Yeah,
managed to
so-
get a measurement there.
You didn't have to go far.
Yeah, we took there's a little hydrothermal.
Cody, what's up,
that
buddy?
I'd like to sample if Rachel, look how swelling. And we took a push core next to it for Ron.
Okay.
But we'll see if she's willing to take the time.
How much time?
One sample attempt, either you grab it and it comes off in
So
one
either
piece,
make a
crumbles,
and
then we're out.
Okay.
But that's her call.
Is she coming back?
Yes, we're doing that, we're gonna do a thermal gradient after, yeah,
Pulse.
thermal pulse after this.
Yep. Okay. Yeah,
But-
she has
but
to
we-
go off at 145.
Yeah, but we had to move to find a place, we had
Yeah.
to move out the line a little bit.
Yeah, it only looks like 10 meters though.
Yeah. But you can see there's some outcropping looking stuff there. There was a little tiny chimney about like this.
I figured that was going to be an issue when we got this close.
Yeah.
It's where the subbottom ran.
Yeah. And we probed 3 or 4 places before we found one where.
Be careful.
So you took the push cores before doing the.
Yes. We took push cords and we couldn't do it people at that site.
So let's try to get 25 meters, and then over.
From directly in front of us or trying to get back on that line?
I think we can. Yes. So let's.
Just somewhere over here?
Yeah.
Are we gonna go chimney next or?
Well, I don't know. I'll have to wait for my copies back.
I will get a.
If she's not back, we'll just move.
Hey, a little off to the left there.
What's it?
A little off to the left.
Oh, yeah, we have to. Hard ground right there.
It's right where you took the push cord.
Yeah, that is. Yeah. Right outside.
Johnny, why do I have a matrix thing up across the bottom of my house? Why do I have the matrix thing across the bottom of my house? Matrix. It's the screen where it's all green. Matrix. It was showing up. Yeah, when you're it's I would imagine it's that well, not specific to that wall, but it was black.
the Nazi elevator. It's,
I did not have.
oh, so that is the overlay computer, but not the input coming to it.
So I think, okay, so it's just another one.
Just over. That's the same camera. But we have notes and no input forward. It's all the levels.
Sit down.
So
Just let them in. Okay, thank you.
Looks like it should be right in front of a tiny mound.
Yeah, it's gonna be an old dead one, if I remember right. It's mostly settlement covered, but it's gonna be hard in there.
Yeah, so we might have to jog further south from there. Yeah. Okay.
But there may be bacterial mat there too.
Yeah. All right. We will see.
We're not-
All right. Well, greetings. Right. So if it's hard as we come on, or that actually is this little vent chimney, dead vent chimney that we think is there, then we'll want to edge to the south to try and find soft. Okay. All right.
So just I want to just go to say goodbye to the
Yep, absolutely.
Spanish viewers. Okay, guys, so I'm going to leave you in the good hands of Dr. Carras for the rest of the dive, probably. I will go and do a ship-to-shore event. And so, yeah, you can shoot him any questions that you have. And I hope to see you all tomorrow. Ahora, para los en español, voy a hacer un evento de barco a tierra en vivo. Entonces vamos a venir por aquí en un momentito más con todo el equipo para mostrar lo que estamos haciendo con CICESE en este caso. Entonces, si tienen alguna pregunta, bueno, pues se van a tener que esperar a preguntarme mañana o preguntarle a Dave en inglés. Ok, gracias a todos por estar y nos vemos pronto. Bye. So, you might want to address James Driscoll.
Yep. I've seen that name for a long time.
Yeah, and then he has a really good, interesting question there. So.
Okay.
Okay.
All right. Well, this is Dave Caress taking over the description on the live feed. As you are well aware, we're at the midpoint of the heat flow transect across, so we are in the vicinity, in the middle of the vent field, and just south of two of the major edifices, and we are having to edge off of our projected line or intended line a little to the south in order to find ground that is soft enough to insert the heat flow probe. And so the move that we are making at the moment is 25 meters along the line. So because we're right in the center where the signal is the strongest, we're sampling at pretty fine intervals. And again, we're having to edge probably 10 to 15 meters off of the line in order to find a soft place. And we're not there yet. There was a question from James Driscoll. I have the curves, or the data we're collecting suggested a trend or correlation to the distance from the vents. And the answer to that is yes. We have the data on the profile that was completed yesterday, 150 meters to the south. And at this point, we've completed half of this profile. And certainly the heat flow is considerably higher in the vicinity of the vents, which is what we would certainly expect. I think the two things that are noteworthy from my perspective, and I am not a member of the heat flow team, and I do not, I'm not ignorant of heat flow, but I don't work with these data directly very much. What I have noted so far is first off that the heat flow values decrease as you move away from the vent much more rapidly in this vent field than they do at the Auka vent field just a kilometer or so to the north, where the heat flow stayed high, particularly on the east side, the basin side. The other thing that we've seen here in this 1.5 profiles so far is that on the west side, which is extending, going shallower up to the west edge of the South Pescadero Basin, the heat flow is a little bit higher than it is on the east side, the basin side, the deeper side. And can't say that I've thought much about the significance of that yet. I guess I would have to admit that if I had had an expectation about that, I would have thought the signal would have gone the other way, for a couple of reasons. One of which is that the crust generally we would think would be thinner as you get more towards the deep part of the basin where the rifting is concentrated. And secondly, where the deeper places where the rifting is concentrated is where I expect the volcanics to be that are being emplaced in the subsurface. But I would guess that that broader context is probably very much overwhelmed by the specific structure locally, and that's really what matters here. Hey, Alejandro. Good to be kind of sailing with you again. So I see a comment in chat from Alejandro Hinojosa, who's one of our colleagues from Sesese, and I had the pleasure of sailing with Alejandro a few years back on a rather small research vessel doing AUV surveys here in the Gulf of California. And actually, I think when Alejandro was aboard, was that not when we were... No, I think that was in the Gulf of California, and it was some of the other Sesese people that joined us off of Ensenada. So, hola to Alejandro. Well, looks like we are probing. I wasn't paying attention. How's that going?
South of the mark, there's definitely not solid sediment there. It's south of that rock.
Okay, so we have moved further south, avoiding a rock, which is a good strategy for a delicate probe. And we are trying to find a good place to poke. And then we're trying it again. Well, looks soft to me so far.
Got you. Right now. Coming out.
Okay.
Yeah. We'll do the normal thing.
Okay.
And then if that doesn't work, then we'll know we'll slide up.
Are we good?
They're good.
Okay.
All right, looks like this is an appropriate place to take a measurement. So we will do that. And the prior measurement and this measurement really are right in the center of the field. We don't have a number yet for the last, not yet. Yeah, it takes Professor Rob Harris a little bit of time to calculate the heat flow results for us back in Colorado. Yeah, there was a question in chat of what is Secesse, and then Barbara S. put up the full name for it. Secesse is a Mexican government research center that's globally known, a very broad-based institute with a lot of people. I don't know exactly how much. A very nice campus, and many of our collaborators work there. So it's quite a nice institute there in beautiful Ensenada, and unfortunately I haven't been able to visit there or haven't found time, or in the last couple of years been able to visit there for a few years. All right, we are inserting the probe. There it goes.
Nice.
Yep, and all the thermistors are coming up nice, so that's going to be a good measurement.
All right, so I got you set up first. 25 away from where the room is supposed to be.
Yep. So,
Hopefully that'll be clear.
Well, now. All right, somebody tell me, what is it? Sea spider? Okay.
Orange thing is part of the body.
Yes, yeah. It's kind of as fun.
Yes.
4.8.
4.8.
Yes.
What was, is that the highest so far in this line? And the highest yesterday, or in the southern one, was 32.
Yes.
Okay, so.
So it's gone down, right? So the last one.
No, the 32 was on the southern transect.
Now, the last one, the top one, getting up to 5, and it's only getting up to 3.5. So
This measurement's going to be lower.
Yeah.
Yeah. Okay. All right. So you said 4.5. Sorry.
Yes.
So
4.8.
4.8.
Yes.
Okay. So the results in from Rob Harris are that the prior measurement at the center of the vent field was 4.8 watts per meter squared. And just for comparison, the central spot on the transect that we did about 150 meters to the south, which was just south of the central edifice of the vent field, was considerably higher. It was 32 watts per meter squared. And so the conductive heat transfer out of the seafloor here at this this point, more on the northerly side of the vent field, is considerably less than just 150 meters to the south, more in the center. question, what are the red appendages under the sea spider? And I was wondering myself, what are the red appendages under the sea spider?
I like it. They look like the front light. I'm not sure that's true, so I'm not going to say.
Okay, so yes, we all are thinking those are. Well, now wait a minute. The fish was not watching where it was going.
It's because the fish can't see.
Well, okay, that is, as Z points out, the fish can't see with all these bright lights on it, and it's not how it navigates anyway. So I do not know what the names are of those structures or their purposes. I would, I as I look at them, I think, oh, those are little arms, and the sea spider must grab things with it and use it to.
But Lisa, who
Oh,
knows her
okay.
stuff, thinks different. So
I've seen a lot.
The red is something it is eating only on the outcrops, rock outcrop. Oh, well, thank you. Thank you, unknown explorer Lisa. Yeah, and as was noted, an awkward eel pout. I agree.
So, then you move 25 meters.
Are you ready?
No.
Oh, okay. Yeah. I'm gonna move 25 forward and slightly closer to the line, assuming that there's a rock.
Yeah, if
outcrop
we
there
can.
as well.
And then
Yeah.
after the next one, we start spacing 50 meters.
Okay.
That's what we can.
Alright. Yeah. So in this one, there's a rock outcrop straight from south, but hopefully we'll be able to move closer to the line.
Let's see it.
Are you doing a heat pulse on this one? Are you- Well, Rob Harris has suggested that I let you know that the average heat flow for the Earth is about 0.06 watts per meter squared.
Hi.
And so
I see
the whole area
is in here. Do you want me to let them
is
in?
quite
Is that
hot.
would that be Stephanie?
Note that the background far away from the vents, hundreds of meters away from the vents, is about 2 watts per meter squared. So that's
Do you want this recorded?
about an order of magnitude and a half higher than the background for the Earth as a whole.
Oh, hello, Hannah. Hi, is this Stephanie?
George is chatting.
There. Can you hear us?
Okay,
Yeah,
so
I can hear
and
you. Hi, nice to meet
George
you. I'm
Matsumoto,
Stephanie.
our education specialist
that? Sorry, I didn't catch that.
at Mbari,
I'm Ian. Ian, nice to meet you.
and a biologist, a research
And we're ready.
biologist.
Great. And we'll
Comments
start
in
letting
the
people
chat
in
that
at the top of the hour.
what's
Stephanie,
getting here might be a red sea pin.
yes,
Those aren't
please.
appendages
I think it would be
as
good to have it.
as the sea spiders don't have appendages like that. At least that he knows of, and George has seen a lot
Hi,
of sea
Raquel, how are
spiders.
you? Hola, Vanessa. Hi, hola. How's work doing?
Okay, let's pull it out, please.
Pulling it up.
Let's do it.
Huh.
Yay, that's great. We were watching the live streaming yesterday and it was amazing. We were like shocked.
So, thanks for the comments about hearing other conversations. We're checking that out. It's not happening here in the control room, so it's happening somewhere on the electronic side. So there was a question in the chat. What is the utility of these heat flow measurements that we are doing here in this vent field? We spent a couple days doing, and we'll spend a couple more days doing.
Oh no.
We're making a move about 25 meters, and we're going to try and edge back towards the desired line, the track line of that subbottom profile. The point of doing these heat flow measurements is really to try and understand part of the processes that are happening in the subsurface. So there's a source of heat somewhere down there in the subsurface. We think that that is volcanic rock that's been emplaced into the sediments. So there's lava that's been emplaced. It didn't get erupted onto the surface, onto the seafloor, but it got emplaced in the sediments. And while it's cooling, it serves to heat up its local area, and that includes the groundwater. Of course, we're in an ocean basin, so the groundwater is going to be seawater, or at least pore water that derives from seawater. And as that seawater is heated up, it becomes buoyant and it rises towards the surface. And so you set up convection cells, hydrothermal convection cells, and where the fluids come to the sea surface, you have hydrothermal venting. That fluid flow that's bringing that heat up is doing a couple of things at least. One of which is it's transporting heat by itself. So you have advective heat transport. And the hot water that comes out at 275 degrees Celsius is bringing a lot of heat with it. And so that's a huge amount of heat transport that occurs through that. But in the subsurface where that hydrothermal fluid is flowing, it is bringing that region to that same temperature, to the 275 degrees or perhaps even hotter. And so you have an area near the seafloor that's in the subsurface that's hot. And as a result, you have enhanced transfer of heat through conduction. And what we're measuring with the heat flow probe is how much heat is being transferred from the seafloor into the ocean via just conduction, right? Not convection, not advection, but conduction. And so that's the other side of the heat transport phenomena here around this vent field. The utility of it for us is that the pattern of conductive heat flow in the vicinity of the vent field and going away from the vent field reflects the processes of fluid flow below, because that conduction radiates away from the places in the subsurface that are brought to the unusually high temperature by the flow of the hydrothermally driven fluids. And so if you have the hydrothermal system structured so that there is a large and broad aquifer of hot water from which the vents derive, then the enhanced thermal conduction will extend over a broad area. Or if what's happening is that there's a single fault, a single zone, narrow zone of high permeability, and the fluid flow is concentrated only along that very narrow zone of high permeability, probably, as I suggested, a fault, then the thermal conduction signal that we measure as heat flow will also be narrowly peaked. It will be high only near to that fault, that zone of high permeability, that concentration of fluid flow. And of course, there's many gradations of this, and there's great complexity of these, intrinsically three-dimensional systems with an unknown complexity of depth. But that's the basic idea as to why what we measure at the surface is important. It's because it's another way of remote sensing, trying to understand what's happening beneath us at depth. In the chat, heat flow, there's a question about heat flow being different than thermal conductivity. Yes, thermal conductivity is an important property of the material that you are conducting heat through. So thermal conductivity is essentially a measure of how fast a material can conduct heat, and or how efficiently it can. And so what we measure with the probe is the thermal gradient. And so there are 5 thermistors on that probe that's 60 centimeters long. It's 5 thermometers, as it were, along in an array, in a line. And generally speaking, we have the ground being warmer than the ocean. The ocean bottom water here is about 2 degrees Celsius. And so there is a gradient as you go from the sea surface that is at exactly the water temperature of 2 degrees Celsius. As you go into the subsurface, the temperature is going to rise because it is hotter within the earth. And how rapidly it rises, well, that is the gradient. And it is the gradient that drives the thermal conduction. And how rapidly or how much flux there is of heat through the seafloor is then controlled by the gradient times the thermal conductivity. So the important point there is that we can't actually calculate the heat flow in watts per meter squared unless we also know the thermal conductivity, unless we also know this basic parameter about the material that's comprising the shallow subsurface here at the seafloor. And part of the measurements that we're making involve determining what that thermal conductivity is. So every time we sit down, we push the probe in and we wait until the temperature readings on the 5 thermistors come pretty close to stabilizing. And at the very least, at a point where we understand how they are trending as they decay towards being in equilibrium with the sediments that they've been inserted into. And then at some of the stations where we want to go ahead and measure thermal conductivity, we then put in a heat pulse. So there's a heating element in the probe, and we inflict a heat pulse into the sediments there at the probe, and then we watch how that temperature spike decays over time. And the higher the thermal conductivity, the more rapidly that pulse will decay and the temperatures will come back down. And so when we do that measurement, then you'll see where right now we've inserted, and the 5 thermistors are rising in temperature, and it's an asymptotic process as they move towards being in equilibrium with the sediments. Are we going to do a pulse on this stuff?
And heat is energy.
And heat is energy. Yes. Thank you, Florian. The important point that Florian just made as he's sitting behind me, running this whole program. So what we were talking about with heat is energy, and this is energy transfer. So in a couple of minutes, maybe 3 minutes from now, Florian will put in that heat pulse, and you'll see the 5 thermistor readings spike upwards and then start to come down. And that is the measurement of the thermal conductivity. So in the measurements where we don't make the thermal conductivity measurement, we're using the values that have been measured on either side. It takes time to make those measurements, and so we only make them as we think that the properties of the seafloor may be varying. All right, well, it's just after 2 o'clock, 2:06 in our local time here on the ship, which is La Paz time, the port that we came out of and the port we'll go back into. And that means we have basically 54 minutes left before we have to leave bottom in order for the ROV to be on deck when it needs to be this evening. It takes a long time for the ROV to go up and down because we are working at great depth. The current ROV depth is 3,685 meters, and to get back to the surface is going to take about 2 hours and 15 minutes, 2 hours 20 minutes, something like that. And it took an equivalent time for the ROV to get down to the seafloor this morning. So working in these deep basins is inherently less efficient than working in more shallow areas because you simply get less bottom time on every ROV dive.
4,500 meters. Right.
I mean, we have 5,300 meters that we go. Or we can technically go down that.
Yeah, we could
just won't work.
Yeah, who knows what's going to happen when we bring it back up.
Yeah. Well, the pilots have been commenting over there. So answering a chat question, what's the deepest the ROV can go? And as Lisa noted, the vehicle is rated to 4,500 meters. When you're talking about something like the ROV or an AUV or anything else you might deploy into the deep ocean, the depth rating you have for that thing is the depth rating of the shallowest rated thing that you put on there. So you might have an AUV that's rated to go to 6,000 meters, but if you put a CTD sensor on it that's only rated to 4,000 meters, then your vehicle's now only rated to 4,000 meters. So every component that's on the platform has to be rated to at least that depth. Another thing controlling how deep the ROV can go is the length of tether that's on the winch. The tether is something where every part of it has to work right. Every part of it has to be functional. A tether is made up of a number of fiber optic elements of fibers, 6 fibers, and several conductors, which is 5. And
Okay,
that.
go out of the seabed, please.
Okay, we are pulling the probe out.
Connectivity seem very consistent, so we just
Okay, so the conductivity or the okay, yeah, you just we are doing the
no. I
okay, so I'm looking at an old plot there. Okay, but you chose not to do the
I mean, the heat pulse always fires because it's programmed to.
okay.
So I have to wait 7 minutes, then automatically the heat pulse fires, and then I decide.
Oh,
if I
okay,
want
but
to-
you pulled out before the
Yeah.
heat. So on the plot, we see the
Yeah.
pulse, but you're not recording it
No.
anymore. Okay. So the choice was to not do the heat pulse or thermal conductivity measurement at that site because the pattern of the shown by the thermistor signals looked so consistent with the prior measurement. So on the fly, Florian made the choice to forego that measurement and save a few precious minutes, which hopefully are going to allow us to get part of an extra measurement here in this remaining 50 minutes of this dive. So with the
So full measurement takes about 16 minutes, and then without the heat pulse, it's 7 minutes.
okay, so the heat pulse takes up 7 minutes out of a full 16 minutes that are required. So it makes a big difference if the choices we make about when to do that thermal conductivity measurement. So the tether again has 5 conductors, copper conductors, wires, and 6 optical fibers, and all of those are in use to send power and commands down to the vehicle and bring back video and data. Every element of that has to work from the winch, the connection made on the winch, all the way down to the vehicle. If there's any flaw in any of those elements anywhere in the tether, then it does not work. And so what happens when you damage the tether? Well, typically that damage occurs towards the ROV, towards the end of the tether, or most often that's the case. And so when that happens, what the pilots have to do is cut off the tether starting just before the point where it's damaged. So you might start off with a tether that's 6 or 7 kilometers long, whatever is the maximum that you can fit onto the winch that you have as part of your launch and recovery system. And then over time, as you operate with that tether, you will lose bits and pieces of it that you have to cut off and then re-terminate to connect the ROV back to the tether. And so over time, the tether gets damaged and it gets shorter and it gets shorter and it gets shorter. Tethers are really expensive, many hundreds of thousands of dollars. So you don't want to replace them any more often than you have to. But at some point, the tether will get too short to do the operations you need to do. And I don't know about the current state with Schmidt Ocean Institute, but most institutes like ours always keep a spare tether, in storage back at the institute, ready to be swapped onto whenever we need to because the existing tether is too damaged.
Yeah, it looks good.
We know that that damage is going to occur when you use it. Question: is it oil filled? These tethers are not oil filled, and they are.
Cement?
Pretty much.
No, they're solid cables built up out of those 11 elements, and then the pilots could probably comment about there are many different designs of tethers, but there will be some outer layers that are designed to protect the what armored layers,
We have two of them,
and there are 2 armored layers around this tether.
and they alternate the way that they're laid on, so that they don't naturally go to turn.
Okay, and so what J-Rod just said is the 2 armored layers are alternated in the sense with which they are put onto the tether during manufacture, so that the tether as a whole does not want to rotate or twist.
On their oil fill thing, I've actually worked on a system that was very old umbilical, and the oil from the termination box came up the fiber optic wise all the way to the top side. You pull it out, the oil, you drop the oil, whatever it just been sitting at oil pressure that long.
That's very interesting. So J-Rod just made another comment based on his quite considerable experience. I think probably both in research, diving, and also industry. You've worked in industry, correct? Yeah. So J-Rod's been out on industry ships and with industry vehicles. So he's seen a lot, and what he was just mentioning was that he has seen a tether that had oil in it, but it was not intended to be so. It was that the oil comp on the deep side, on the vehicle side, that oil penetrated into the tether and actually rode all the way through the tether up to the top side, and oil came out at the top. That was, he said, a very old system. Question: do ROVs share the same type of tether cabling, or does each ROV have its own custom built? It's a combination. There are a number of types of ROVs that many are built like that and have similar tethers. So there are going to be a lot of systems that have a fair degree of commonality. There are many different manufacturers of subsea vehicles and ROVs in particular around the world. But certainly there's going to be certain models that are widely used and have commonality in design and parts. However, on the academic side or the research side, there is a real tendency for the vehicles to be, the vehicle systems, the ROV systems, including their launch and recovery, to be customized to particular ships and the particular uses that those institutions are planning on engaging in. And so for Mbari, for our 2 ROVs, the Doc Ricketts, which is a 4,000 meter rated system, and Ventana, which is a 1,850 meter rated ROV, our tethers are custom built for those ROVs. I don't know about SOI. Are yours custom?
The tether?
Yes. And the answer is yes. So the tether used on the Falcor with ROV Sebastian was designed for this ship, for this launch and recovery system, and for this ROV. So they specified how many conductors, how many fibers, how much armoring, how long it was going to be, and it was constrained by the winch that they have as to how thick it could be, and there are several other factors that go into making the design decisions for something like a tether.
Ours is 19 mil. But the breaking strength is 20 tons.
Okay. 19 mil. So the tether is 19 millimeters in diameter, and it has a breaking strength of 20 tons. Starting to work out the other side. So we are back on to the sub-bottom line.
Or would you like to go next?
50 meters. Yeah. They keep on 50 meters. When it's k's away, then we start maybe 100. It's very funny because somehow the temperature gets lower.
On this side.
On this side, on the end, it's
That's a
It's
This has been a consistent correlation.
I already sent that email to Victoria before we started.
Yeah.
So, because I think they last time they did also a few measurements, but just the experiment measurements, and then they always put in where it's hot. Like here, it's not that interesting, but
okay. Yeah,
it's
that.
not here.
Yeah, it's an interesting point. So Florian just made a comment that it's somehow strange that where the ground is warm is where we're seeing a lot of life, and it's not that these are chemosynthetic communities. This is there's some clams around, but there's not really a lot of venting right here. Nonetheless, this is where the animals are, and it's actually warmer on this side, it looks like, than it was on the other side. We're right now making 50-meter moves between the different sites. There was a question in chat, does Schmidt Ocean Institute have manned submersibles? And the answer to that is no. They don't. They've chosen to focus on the ROV as the platform that they have permanently available on the ship. But then the other thing that SOI does in having various science groups come aboard and execute science programs that have been proposed, in many cases, these science groups will bring their own platforms, particularly AUVs. That's certainly what we did in 2018. And there have been many instances of AUVs operated off of the Falcor, AUV Sentry from Woods Hole Oceanographic Institution. The Southampton Ocean Center has brought their vehicles on board. University of Tokyo, I think, has been here, or perhaps it was Jamstec. And a number of others. So SOI doesn't own all the equipment that gets operated off of this ship. They have a ship that's well suited to serve as a platform for people to bring their own equipment and operate it off of this ship. Manned submersibles are not as common as they used to be. Because of the great utility of unmanned robotics, whether tethered and interactive like an ROV or autonomous like an AUV. The manned submersible, of course, that we're most familiar with and that many people have worked with is Alvin, which is operated by the National Deep Submergence Facility of the Woods Hole Oceanographic Institution. And Alvin actually has recently been upgraded to go deeper than it's ever gone before. somebody will probably correct me because I'll get this wrong, but I think it's 6,500 meters that it's rated to now. So certainly manned submersibles still are used and have an important role in ocean research and ocean exploration. But on a day-by-day basis, most of us use ROVs much more commonly. What's that?
I think Ben's the only railroad that has any banks.
Okay, well, this guy over here has been down many times. In a number of different, you've been, yeah, in many different submersibles. He's done Pisces. He's,
No, I've never been to Iceland, just Seacliff.
okay, Seacliff and Elway, right? Okay, so just commenting there, among us, Z has a fair bit of experience. He's been down in both Alvin and Seacliff, studying hydrothermal vents. So there was a comment there from Connor Johnson that he would much prefer to be somewhere where it's a few C warmer than if you lived in a 2 degrees Celsius environment. Well, that's so a lot of animals prefer that too, in a kind of interesting way. One of our projects at Mbari is studying a place that's called Octopus Garden that is on the east flank. It's really just east of Davidson Seamount. I shouldn't say it's on the flank. I think we've demonstrated that the little ridge that's Octopus Garden is not actually part of the Davidson Seamount edifice itself. But it's a place that's about the same depth as this, about 3,400 meters. We're at 3,600 meters. And there is warm water flowing out of the ground there. It's not hot water. It's about 5 degrees warmer than ambient. So instead of 2 degrees Celsius, because the temperature there is about the same as it is here, the water that comes out of the ground at Octopus Garden is about 7 degrees Celsius. So it's not volcanically driven. It's driven, we think, by simply deep crustal circulation of groundwater. But on this little ridge, along the ridge, there's warm water seeping out, just a little bit warmer than ambient. And if you go there, this was discovered by RV Nautilus with their ROV Hercules, operated by the Ocean Exploration Trust out of the University of Rhode Island. 3 or 4 years ago, they did an explorational dive there, and they came upon this place where there were hundreds, thousands of brooding octopus. And so the female octopus will lay their eggs, they'll mate, they'll lay their eggs, and then they will lie upside down on top of those eggs and protect them until the eggs hatch, and then the females die. It takes a long time for those eggs to brood because the water is so cold and the metabolism is so slow. So it takes years sometimes for deep sea octopi to brood their eggs. And what was determined, or is really kind of just now being determined from work done with NOAA, the Monterey Bay National Marine Sanctuary, Ocean Exploration Trust, and a lot of work from us at Mbari. The reason that those octopi are brooding there is because they get an advantage out of doing it in the very slightly warmer water, just a few degrees, and that decreases the amount of time it takes the eggs to brood and the new octopi to hatch by months. So it goes for substantially reduces the amount of time. I'm not giving you the numbers because unfortunately, as I sit here, I realize I don't remember the numbers that I was told a few weeks ago when I was between cruises. But the biologists led by Jim Barry of Mbari have figured out how much of an advantage brooding in the warm water gives these octopi. And so, yeah, animals really do like warmer water, at least in certain contexts. Yeah, thank you, Lisa. Up to 4 years. There's another species of octopus that's been observed to be somewhat longer than that, but 4 years is probably about right for the species there at Davidson. And I'm not giving you the species name because I would just mess it up. Sure. If George Matsumoto is still out there, he'll answer. All right, so Z, looking out here, I see a lot of not living clams. Do you think that there is active diffuse venting here?
Well, the clams don't necessarily need hydrothermal fluid because there is sulfate reduction going on in the subsurface that they can live on. So they need organic matter rich sediments. But if there's even a little higher heat flow, we're speculating that slow advection just brings up the deeper resources, so they're more abundant. And if you zoom in there, you would see that there were some live clams, but not as many as you see dead clam shells. So this area does have live clams in it, but it's not probably as advective as it was when all of these dead clams are alive. The clam shells are made of calcium carbonate, and at this depth, even though these mounds are made of calcium carbonate is actually undersaturated or will dissolve. And so the fact that these clam shells are still here tells us that it can't be too old. Unfortunately, I can't put a real number on that, but previous studies on clam dissolution rates at hydrothermal vents suggest that clam shells could last 50 to 100 years, but it really depends on the chemistry of the bottom water. And because we're very deep here, the deep water can hold more CO2 under high pressure. More CO2 means more acidity, and that's why the surface ocean is saturated with calcium carbonate. So critters can make calcium carbonate shells at the surface, but at depth, because you dissolve more CO2,
You might want to read Rob's comment.
the acidity goes up, and you eventually get to a depth at which calcium carbonate disappears. And where it completely disappears, we call that the calcium carbonate compensation depth.
Well, thank you, Z. We've moved on, so, well,
Yeah,
and
maybe the biologist can. Just because. Oh, okay.
But if we go down, we're going back to the mud, right? Just run this far off.
Sure.
So just so you know, I don't know if it affects your reading.
Yeah, maybe we
Just
we
up
can
and down.
right now. No, maybe we can right now just go up and down and just try to get off.
I was flying around like a crazy man on the way up. It's going now.
yeah,
Oh, okay, it's off.
mostly, yeah.
Yeah.
One of the commentary here over the last couple minutes, the heat flow probe had picked up a lot of sticky mud on it, and there's concern that would mess up the next measurement. However, the pilots are quite adept at flying the ROV in such a fashion that it washed off the mud. So that is a problem solved. There is a comment up there. Oh, I'll just this came from down the row here in the control room. That mapping wise, you can mount multi-beam systems sideways onto ROVs and AUVs in order to map things like overhangs and steep cliff walls. And so just to amplify that, one of the things that my group is working on is trying to survey at basically centimeter scale, and we do that from ROVs, and we do that with a system where we have a sensor frame that combines a multi-beam sonar, a LiDAR, stereo cameras with strobe lights, and an inertial navigation system. And that's all on a single frame. And then that's in a big tool sled under the ROV, and it rotates so that it is always facing perpendicular to the seafloor. And so if we're on a vertical wall, then that frame is facing forwards. And so with that kind of a configuration, we are capable of mapping complex terrain, such as the structures that we've seen on these edifices. And in fact, our intent and our schedule is to be back here in South Pescadero Basin in April with an Embari ship doing that kind of mapping off of our ROV, the Dock Ricketts. So it's our plan to be back here at JaichMaa vent field with that mapping system in just a few months.
I've never talked about it on the sort of television shows. So part of the sort of rear.
With the scatter? The guard?
The guard part, yeah.
Yeah, I don't know the proper name for that. There's, I think if you have just one thing coming out, it's a tang.
The tank is the part that goes down into the hand.
Yeah, okay.
That's the tank.
All right.
Ready? All
Yeah,
right.
thank you.
We need to build one of those.
And there goes the probe again. So I think we're about 100 meters east of the vents. Is that right, or a little further?
I'm not sure.
You're just making moves, and we'll plot it up later. Yeah, but we're about 100 meters or so, maybe a little further from the center of the vents. Yeah. Ask a question, and you shall get 120 meters measured directly on the map. So we're working our way eastward. The last heat flow value was?
The highest 7.3.
Was 7.3. So here we are, we're working away from the vents, and the heat flow is going up, as you can imagine. That's an interesting signal. We need to get the rest of the picture before we can pretend to start making sense of it. Yeah, there was a comment about some high resolution mapping work that's been done off of Hercules on EV Nautilus. That references the looking for the Amelia Earhart's plane. Actually, I guess that was multi-beam that they did for that. They stood off a fair bit, but OET on the EV Nautilus has a long history of doing very high-resolution mapping, led by Chris Roman, a professor at the University of Rhode Island. And going back quite a few years, Chris and his group have operated with a mapping system combining very high frequency multi-beam sonar and a structured light system. And that's where you have a laser fan, so it's a continuous laser, and it makes a fan that then is directed at the seafloor, and you watch it with a video camera. And you have to know the geometry of the camera and the laser really, really well. But if you calibrate it really well, then you can watch the bright line that is the intersection of the laser fan with the seafloor and calculate that topographic profile. And then as you move along, you can observe very, very high resolution bathymetry. And so Chris has done some, and his group have done some amazing work over the years. I think the maps that have been best known are those he's done over shipwrecks in the Mediterranean, showing fine details of amphora and other artifacts that are part of ancient shipwrecks. But they've also done similar work in many other contexts, particularly including habitat mapping in sponge and coral communities in the deep ocean. Okay, well, it's 2:42 here in local La Paz time, and that means that we have 18 minutes left, more or less, before we have to leave the bottom. And so we're hoping to get one more heat flow measurement in here today. And I think what we'll be left with here is we absolutely have not completed this profile because the heat flow is so high here on the eastern side, and we're going to need to continue it till we get far enough that it goes back to the local background level.
Whatever you like. Is that what you want to do? Do you want to go continue to go for?
I would like to do a full measurement here. It takes 7 more minutes, and then a short one, 20 meters, 25 meters back, and then should be done. I think we finish at 3, maybe 3 and 2, 5 minutes. I don't know.
Yeah,
Thank you.
That won't be a problem at all.
Just
Okay,
25
cool.
meters.
Thanks.
Yeah.
But 25 meters back is what he said, right?
Yes.
Right. So he's trying to
now
go
it's the
back
X.
and fill
Okay.
in a more
Let's
detailed.
go 25 meters back and see what's changing, right?
Yeah.
Then
Yeah, I think that's a good call for you. It's a very interesting signal here. So, actually, what we're going to do for our last measurement of the day is move back along the line. We had moved 50 meters forward, and it's still pretty hot here. And so we want to move back and fill in a measurement 25 meters back or halfway in between prior measurement and the most recent one. And have that higher detail here where the signal is changing rapidly.
Okay. That's
Well, the pilots are scanning around, and you can see the seafloor in our vicinity here. Does have some interesting texture to it.
Cody was on earlier. Cody was on earlier. Hey, Ben, what's that? I can't be bothered. I don't know how to look here.
So my compatriot down at the end of the table there has been putting some points into chat. Talking of gold in science, there were some comments about looking and finding for gold, looking and finding gold. And so what he wrote here was, talking of gold in science, the very first German meteor expedition was supposed to look for precious metals in order to pay for World War I reparation. Not something I have known. There's a current German ship, research ship called the Meteor. I've not been on it myself. I nonetheless have a T-shirt that was given to me by one of my University of Bremen colleagues. But that is one of the pioneering oceanographic research vessels, and the Germans still use that name on ships. There's always a polar stern. There's always a meteor. Yes?
The benefit was they did cross-Atlantic transect, continuous transect of oceanography at almost every few degrees in latitude. So one of the most complete data sets of the Atlantic Ocean from above the equator down to almost the Arctic at the time.
Okay. And then a further comment on the subject of the meteor was that although they were sent out there with a goal to find precious metals, what they actually accomplished, which from our perspective, of course, is more important, was amongst the first continuous set of oceanographic measurements across and along the Atlantic Ocean. What I think you just said is they went north to south
Attitudes.
Oh, a different. Okay, so they did latitudinal transects across the Atlantic at a number of different latitudes, extending from above the equator down into the Southern Ocean, which which was a pioneering and foundational set of observations.
Okay. Go out of the center, please.
All right, we've completed that measurement. Now we are going to back up 25 meters and make one last measurement. And then we shall be done for the day.
Here.
Better for my hands. Feelings? Feelings?
Well, in addition to seeing the chat associated with the YouTube stream here, I'm also watching a different chat stream, Slack stream actually, associated with the heat flow team ashore and out here. And one of the points that came across about a minute ago was that we really have to think about what we're going to do tomorrow in the context of what we've seen today. And so that's correct. And the reason it's correct is because what we've observed today is a bit surprising. And we need to adapt our plan to do the best job tomorrow, capturing the signal that's here, that is different than what we expected, that it's hotter here on the north end of this vent field. It's hotter on the east side than it is even in the center. And so there's something going on at depth that's causing the locus of conductive heat transport to have a different pattern than the surface expression of the vents. And so we need to think a lot about how we can define that signal with the limited time that's available to us. And that's a lot of what happens on these kind of trips, where you're making observations that nobody has ever made before, and therefore, in a sense, you may be looking at ground that people have been at with ROVs before. But even just any observations you make that are different than what's been possible before, that's exploration. And that's really what the heat flow team is engaged in here today and this week.
Let's discuss it later.
Yeah. So I just saw the email.
Yeah,
Cool.
Well, so Lisa comments, I'm sure it's a pain in the butt for your plans, but I get excited when findings from one dive change the plans for the next. Well, yes, that is absolutely how we feel about things. We generally, I guess I should speak primarily for myself here and not other people that do a better job of planning. But it is important to have a plan. But it is more important to know what your priorities are, what you're trying to achieve, and you need to make up the plan on the spot. You need to adjust things always to reflect the reality of what you're observing, and that's in one of the an outreach session yesterday with I believe middle school children. I was asked what I like most about what I do, and my answer was it's the explorational aspect of it. It's the surprises. It's the finding out things that nobody's ever found out before, and just that it's that is what is so motivating for me, and what is such a huge privilege to get to be a part of.
So from 7 to 3 to 7 on the patch.
Yeah.
3 just
On the other side. Interesting.
So let's see what's
Yeah.
like.
That's a big difference.
It's huge difference. But I need to double check if there's
Okay.
if we see maybe that the base
Move back about 25 meters. Now we're going to try and set down.
Potential explanations, but still.
The mud didn't come off.
Yeah.
Yeah, we couldn't clear the mud off at this time.
We tried. You're gonna try to use this.
Longer, good. They couldn't get the mud.
that's fine. Okay, just go down and take the measurement. It's not a problem.
Yeah, what we were just talking about here on the heat flow probe got sticky mud on it again, and the pilots came up off the bottom a fair bit and rotated and basically tried to blow it off. And this time it's stuck. It hasn't come off. We're just going to go ahead and take the measurement. Yeah, it just, now we know the mud here is really, really sticky.
And it's definitely like at a deeper depth, like.
A comment there, unexpected findings are always interesting. It'd be cool to see it plotted out to see if it correlates with features on the seabed. Absolutely. But also under the seabed. That's one of the reasons, again, that we're doing this profile or these profiles along particular lines. That's because these are track lines of AUV surveys where we have subbottom profiles that show us the structure in the subsurface, or just 2D images, slices of the structure of the subsurface structure down to about 50 meters depth below the seafloor. Question about the suction sampler. So the suction sampler is definitely on board, but it's not on the ROV. That will be equipment that will be integrated with the ROV next week for next leg for the biology and microbiology dives. Yeah, and as far as getting the mud off, the pilots and the heat flow team were contemplating using that wand, or not wand, but the rod that you that we use to test whether the bottom is soft enough. They were contemplating reaching around with that and trying to scrape it off, and then the recognition that that's more likely to cause problems with the probe than to solve problems with the probe. So we chose not to do that, and just go ahead and take the measurement, and we'll see.
Yeah, it's too far back for us to use even section sample values for that region.
Okay, and just Chris noted that even if we had the suction sampler on the ROV, the geometry isn't good. You wouldn't be able to reach back and down to clean off the heat flow probe. It's on the side of the vehicle and back far enough that it couldn't really get reached. Connor has noted the heat flow probe has come out different every time, and that's right. There's quite a lot of variability in how the mud sticks to it or not. In it goes. So this will be the last measurement for today.
You should give them some eye candy.
What's that?
You should give them some eye candy before we leave.
No,
You can do it.
all right. How does this work, Z? You know I don't run the camera.
Here,
I run the sonar, not the
you
camera.
talk and I'll drive.
Okay. Yeah. See, Mr. The expert Z is going to drive the camera for you. And I guess I need to, on the way up, I need to do a little self-training here and figure out how to operate this equipment.
This is the little, it looks like the one that George identified for us.
Yeah, it's always neat to see the tracks that the various benthic animals leave behind as they maneuver around, and you see that deep track there. That's a clam. The clams move around. Don't know why they move around, but they do. And we see that in chemosynthetic clam communities that are cold seeps as well. One of the first observations we had that really told us that a LiDAR had utility for seafloor mapping was the first time that we leased and tried a prototype LiDAR system. We used it at a chemosynthetic clam community at 2,850 meters in Monterey Canyon, and when we processed the data, we discovered that we were mapping the clam trails that you couldn't even see in the ROV video. And so
Evidence of carbonate dissolution.
oh, and as Z is pointing out, in that clamshell that we're focused on right now, you can see a hole, and that is because that carbonate clamshell is being dissolved by the seawater, because the seawater at this depth is undersaturated in carbonate.
Clam siphons and anemone.
Okay, and then there are two clam, I guess, is it one or two?
It's two.
Two
I
clam
think.
siphons in the center left, and then next to that, further left, is an anemone. All right, well, you can see we're getting a really solid temperature measurement. It's good 4.5 degrees or so on the deepest thermistor.
Okay, that's a single clam.
All right, that was a
My bad.
scrolling over. There's the siphon of a single, mostly buried chemosynthetic clam. So that's what they look like when they're alive.
I know what clam this is. I just gotta think of the name.
The Vescamiids, they're not.
No, they're not the best clams.
Yeah, so Vescamiid clams are the ones at the Monterey Cold Sea. Yeah, I don't know.
It's not going to come to me. I'll think of it tomorrow. It's not part of the clam, but because the clam is circulating things, there's bacteria. Other things are taking advantage of what the clam's doing. So I don't know what that slime ball is. It's slime tail, but it's probably microbial.
So Connor commented,
Moving nutrients around.
is there a depth component to calcium carbonate levels in the ocean? After a certain level, the water is deficient and isn't conducive to shells. Yeah, it's one of the fundamental observations of the nature of seawater in the oceans is that carbonates are stable in the upper part of the oceans, and if you get deep enough, they start to dissolve, and the transition is called the calcium carbonate depth, and it's not at the same level around the world. It varies, but below the CCD or calcium compensation depth, below that, things made of calcium carbonate, like mini shells, will dissolve. And
That was his back.
one of the basic consequences of that was explained by that was that sediments in the deep ocean are primarily siliceous because all the carbonate material is dissolved, and so what's left are the silica-based shells from things like diatoms and other plants and animals. So carbonate sediments can only accrue in relatively shallow waters. Does anybody know what the CCD depth is in the Gulf of California?
Yes.
No, I'd like to know that. Actually, the CCD depth is the depth at which all the shells from the surface finally dissolve and don't make it to the seafloor. The depth at which calcium carbonate goes from from oversaturated to the surface to under is called the lysocline,
Oh, okay.
I think.
I should have taken an oceanography class.
Me too.
All right. Okay, so we are done with that final measurement, and we are going to be coming off of bottom. Okay. So we are actually done, right?
Yes.
Off bottom.
Okay.
So yes, go ahead and
Yes,
bring us
thank
off
you.
bottom. And
Thank you, guys.
thank you very much, guys. That was a great day. Okay, well this has been our third dive on leg 2 of expedition FK 210922, interdisciplinary study of hydrothermal vents in the South Pescadero Basin of Gulf of California. And we're still, for the moment, at a depth of 3,687 meters. They're going to stow the poker and then bring us up. And the bringing up will occur at somewhere between an average of 25 and 30 meters per minute. Partly that depends on the ballasting. We didn't collect a lot of samples, so the ROV is probably not going to be unusually heavy, so it might be a little faster than otherwise. If we'd picked up a lot of rocks and so forth, then coming up would be a little slower. But it's going to take about 2 hours and 15 minutes or so before the ROV is at the surface and can be brought onto deck.
Okay, guys, so just signing off for today. As Dave pointed out, it was a great day. We're very happy. We are truly grateful to the pilots, our amazing team here that made this possible, along the students and everybody here. So thank you. Please come back tomorrow for more action from Falcor. Muy bien, pues después de un gran día de mediciones, nos despedimos por el día de hoy. Por favor, regresen mañana para otro día completo de acción. Le tenemos mucho agradecimiento a nuestro equipo de pilotos, estudiantes y técnicos que nos han ayudado en esta expedición, y obviamente a ustedes, audiencia de YouTube, que hacen que esto sea muy interesante. Nos vemos mañana. Bye.